What if the universe gave us a cosmic replay button? Not a metaphorical one, not a recording, not a simulation, but a real, physical replay of an event that happened billions of years ago. What if, somewhere out there in the darkness between stars, a natural mechanism existed that allowed us to watch the same explosion twice, or even more times, all from different angles and at different times? This isn't science fiction. It's science. It happened. And the cosmos was the projector, the lens, and the screen. But before we continue, subscribe to the channel. It all began with a flicker of light. But this wasn't just any flicker. It was a supernova, a dying star's final act, a burst so bright it can outshine an entire galaxy. It originated in a galaxy over 9 billion light-years away. And yet, by a twist of cosmic architecture, we didn't just see it once. We saw it multiple times. At different moments. In different places in the sky. Not because the star exploded more than once. It only exploded once. But the light itself was bent and redirected, stretched through the geometry of space by a colossal intermediary, a massive galaxy cluster sitting in just the right place. This galaxy cluster acted like a funhouse mirror, not only distorting the image of the distant galaxy but also splitting and rerouting the light. The effect? The same event, one cosmic flash, appeared again and again, with each path taking a different amount of time to reach us. We saw echoes of the same moment, replayed by the universe itself. It was like the cosmos whispered, "Watch that again. And again." Not because we built some telescope that could record time. Not because we sent probes into the past. But because gravity bent light in such a precise and extreme way that the same photons from a single supernova arrived at Earth at staggered intervals, years apart. This wasn't just rare. This was unprecedented. A visual echo across space-time. A cosmic deja vu. The idea is so strange, it almost sounds mystical. But it's not magic, it's physics. Einstein predicted it over a century ago. And it came true in the strangest way possible. The universe revealed to us something profound, that time, light, and gravity are interwoven in ways we're only just beginning to understand. It gave us a glimpse of something once thought impossible, a naturally occurring, perfectly timed, scientifically verifiable cosmic replay. Welcome to the story of Max J1149. Welcome to the universe's own highlight reel. To meet the protagonist of this cosmic story, we have to set our sights unimaginably far into the distance, across space, and across time. Over 9 billion light-years away, long before Earth had even formed continents, a galaxy named MACS J1149 emitted light that began a journey toward us. That light traveled for nearly 3/4 of the age of the universe, passing through the expanding fabric of space-time, until one day, it reached our telescopes. But we didn't see it as it is now. We saw it as it was back then, when the universe was still young, still forming its large-scale structures, still cooling from the heat of its early chaos. MACS J1149, like many distant galaxies, exists as both a window into the deep past and a question about what galaxies looked like in those early epochs. But what made MACS J1149 so extraordinary wasn't just its distance, or its age. It was the way it reached us. Instead of a direct line of sight, its light passed through something massive and ancient, a galaxy cluster far closer to us in cosmic terms. This cluster didn't just passively let the light go by. It actively bent it, distorted it, redirected it, and magnified it. In doing so, it created something extraordinary, a lens, not made of glass or mirror, but of gravity itself. Thanks to this gravitational lensing, we weren't just looking at a tiny speck of light lost in the blackness. We were seeing a magnified, warped version of a galaxy so distant that, without the help of nature's optics, it might have remained invisible forever. What reached us wasn't a single beam but many fragments, scattered and stretched by the intervening cluster, producing multiple images of the same galaxy across the sky. MACS J1149 was now more than just a remote speck. It became a kaleidoscopic display of cosmic geometry. One galaxy, seen in several places at once, its light echoed and warped across space by a natural lens we didn't build but simply happened to observe. And that coincidence, that alignment, would go on to reveal something even stranger, not just a distorted galaxy, but a repeating explosion, a cosmic event so powerful, it forced us to rethink how we view time, light, and observation itself. Max J1149, in this sense, isn't just a galaxy. It's a message from the early universe, written in twisted beams of light. A message that took billions of years to reach us, and when it did, arrived not once, but many times. Between us and the distant galaxy Max J1149 lies a colossal structure, one of the most massive objects in the known universe. This is the galaxy cluster Max J1149.5 plus 2223, and its role in this story is absolutely pivotal. It didn't just block the view of the distant galaxy, it transformed it. Galaxy clusters are gravitational giants. Made up of thousands of galaxies, vast quantities of hot gas, and an even greater mass of invisible dark matter, they collectively create an enormous gravitational field, one so powerful that it warps the very fabric of spacetime around them. This warping doesn't just tug on stars and galaxies nearby. It bends the path of light itself. When the light from Max J1149 traveled toward us, it encountered this cluster along the way. Instead of moving in a straight line, that light curved. Like rays passing through a magnifying glass, the light was focused, magnified, and, most importantly, split. The gravitational field of Max J1149.5 plus 2223 acted as a cosmic lens, reshaping the trajectory of light beams based on their paths through space. Some paths were direct and relatively quick. Others were warped, taking longer routes, looping around denser regions of the cluster's gravity well. These differences in route length and gravitational intensity caused the light to reach us at different times, even though it all originated from the same distant source. This wasn't just distortion, it was duplication. Max J1149 appeared in multiple locations across the sky, each one a warped, time-shifted version of the same galaxy. The effect is like looking into a cosmic funhouse mirror made not of metal and glass, but of dark matter and gravity. The universe itself became the lens, the mirror, and the theater. The magnification from this cluster was also crucial. Max J1149 is unimaginably far away, and under ordinary circumstances, its light would have been too faint for us to detect with clarity. But through the lensing effect of Max J1149.5 plus 2223, the distant galaxy became significantly brighter and more detailed than it should have been, allowing astronomers to study its features in a way that would otherwise have required technology far beyond what we currently possess. And it's not just about brightness. The light that was split and delayed by the cluster's gravitational lensing offered more than just a better image. It gave us a way to study time itself. Because every path the light took was affected differently, scientists could effectively time travel by watching when each light beam arrived. This cluster wasn't just in the right place at the right time, it was a cosmic instrument, naturally positioned in the precise alignment needed to turn the universe into its own observatory. Without Max J1149.5 plus 2223, we would have missed the event entirely. No rerun. No echo. Just one bright flash lost in the immeasurable darkness. But because of this cluster, this cosmic magnifying glass, we saw something no human had ever seen before. We saw the same explosion more than once. To understand the profound strangeness of what happened with Max J1149, we have to go back to one of the most revolutionary scientific ideas ever proposed, Albert Einstein's general theory of relativity. Published in 1915, general relativity didn't just change how we view gravity. It redefined what gravity is. Einstein proposed that gravity isn't some mysterious force pulling objects toward one another across space, as Newton had thought. Instead, he described gravity as the result of mass and energy curving the fabric of spacetime itself. In his words, matter tells spacetime how to curve, and curved spacetime tells matter how to move. Now imagine spacetime as a vast, flexible rubber sheet. When you place a bowling ball on that sheet, representing a massive object like a star or a galaxy, it creates a deep dimple or curve. If you then roll a marble across the sheet, representing a beam of light, the marble's path will curve as it approaches the bowling ball's depression. Not because the bowling ball is pulling the marble directly, but because the surface itself is warped. This analogy, while simplified, helps us grasp the essence of gravitational lensing. Massive objects don't just attract matter, they also warp the paths of light passing nearby. The more massive the object, the greater the curvature. And when a truly massive structure, like a galaxy cluster, lies between us and something far behind it, the result is dramatic. The light from that distant source, which would normally travel in a straight line, now bends as it encounters the warped space around the intervening mass. This bending doesn't just alter the direction, it stretches, magnifies, duplicates, and even time shifts the light. It turns space into a lens. Gravitational lensing comes in several forms. When the alignment is perfect and the masses are colossal, it can create phenomena known as Einstein rings, complete or nearly complete circles of light surrounding the lensing object. When the alignment is close but not perfect, we often get arcs or multiple images, sometimes arranged in crosses or clusters across the sky. These are the fingerprints of gravitational lensing, visual distortions not caused by optics in a telescope, but by the warping of reality itself. MACS J1149.5 plus 2223, the galaxy cluster responsible for lensing MACS J1149, is so massive that it doesn't just create one distorted image. It creates several. The combined gravitational pull from its galaxies, gas, and immense amounts of dark matter acts like a wildly complex, ever-shifting lensing field. And here's where it gets even more extraordinary. Gravitational lensing doesn't just alter space, it affects time. Because general relativity tells us that time is part of the same fabric as space. Warping one means warping the other. Light traveling near a massive object moves through regions of deeper gravitational potential, essentially, deeper dimples in the rubber sheet. This means it takes more time for light to pass through these regions than if it were moving through flat space. So not only do we get duplicate images from different paths, but those duplicates arrive at different times. Think about that. Light from a single event, a star exploding in the distant galaxy MACS J1149, can reach us in stages. One path may be slightly shorter, another slightly longer. One may loop near the heart of the lensing cluster, while another grazes its edge. These path differences, though tiny on a cosmic scale, translate to days, months, or even years in arrival time when the distances involved are measured in billions of light years. This concept was once purely theoretical. In 1936, Einstein himself was persuaded to publish a short paper on the topic of lensing, dismissing it as unlikely to ever be observed. He couldn't have imagined the precision telescopes we'd build or the cosmic alignments we'd one day witness. Fast forward to modern astronomy. Thanks to instruments like the Hubble Space Telescope, gravitational lensing has become not only observable, but a powerful tool for discovery. We use it to map dark matter, an invisible substance that outweighs visible matter but doesn't emit or absorb light. We use it to study galaxies too faint or distant to be seen directly. And, as with MACS J1149, we use it to witness the same event more than once. What's important to realize here is that this isn't some trick of optics. It's not like putting on a pair of weird glasses that show you two versions of the same object. The multiple images caused by gravitational lensing are real. The light paths are distinct. The arrival times are different. And the physics governing them is beautifully precise. In the case of MACS J1149, the galaxy cluster didn't just magnify and duplicate the background galaxy. It created multiple, staggered arrivals of a supernova. A single stellar death echoed across spacetime like the delayed sound of thunder after a lightning strike. We're not used to thinking of light as something that can arrive late. Light moves at the fastest speed in the universe. But when spacetime is curved, light no longer follows what we'd consider a straight path. And in such curved paths, the fastest route may not be the shortest in time. In fact, the fastest route may be one of the slowest to arrive, depending on the gravitational terrain it travels through. This realization, that light can take multiple routes and arrive at different times, was the gateway to the extraordinary discovery that would soon follow. Because in 2014, one of those light paths carried something special. Not just the image of a distant galaxy, but the last flash of a dying star, a supernova whose light had been split and scattered across the sky, waiting to reach us in waves. And when that supernova was first seen, astronomers realized they were looking at more than just an explosion. They were watching a cosmic echo. A moment replayed, delayed, and scattered by the universe itself. When the light from MACS J1149 began its journey toward Earth, it was carrying more than just the glow of stars and the whispers of cosmic dust. It was also holding within it the story of a galaxy distorted not by its own doing, but by the immense gravitational hand of a structure it passed on the way, a galaxy cluster that twisted light into a spectacle of duplicates and delays. This is where the real wonder begins. We didn't just see MACS J1149 as one blurry dot in the night sky. We saw it scattered across the heavens. Not because there were multiple galaxies, but because the same light was being bent, stretched, and split, so precisely and so powerfully, that we were given the illusion of multiple galaxies. In truth, every image was of the same galaxy, but each version arrived at Earth from a different path carved through curved spacetime. Each path the light took acted like a separate corridor through the cosmos, some more direct, others winding and looping through the dense heart of the lensing cluster MACS J1149.5 plus 2223. Just as sound can echo off canyon walls, arriving at your ears in waves and intervals, light can echo through the gravitational terrain of the universe. Each image we see a different note in the same symphony. The result? A mind-bending cosmic mirage. Through our telescopes, we saw arcs of light stretched across the sky. These were not disconnected phenomena, but time-split, distorted versions of MACS J1149. The gravitational lens acted not like a single piece of glass, but like a fractured prism made of dark matter, galaxies, and interstellar gas, each shard bending light in its own unique way. The geometry of the lens was so intricate that it didn't just produce one duplicate. It produced several. Each one was from the same galaxy, yet each arrived from a path slightly different in distance, curvature, and gravitational delay. Think about what this really means. Imagine walking through a hall of mirrors, where every reflection of yourself is not only positioned differently but delayed in time. You raise your hand, and one mirror shows it instantly. Another shows it a moment later. Another still is delayed even further. Now replace mirrors with entire arcs of space curved by gravity, and replace your reflection with light that's traveled billions of years. That's what we observed with MACS J1149. These weren't just duplicates in appearance, they were duplicates in time. Each image of the galaxy arrived not only from a different angle but from a different moment. The galaxy itself hadn't changed. It was our position in space and the layout of the intervening gravitational lens that determined when and how each beam of light arrived. This creates something deeply counterintuitive, an astronomical observation where time becomes location. Where, looking left, might show you the galaxy as it was one day, and looking right, shows it as it was a year earlier or later. All of these moments existed in the same sky, all at once, separated only by the paths their photons had to travel. It's hard to overstate how bizarre this is. We are used to seeing things as they are, or as they were, given the time light takes to travel. But what gravitational lensing showed us was that time itself can be sliced, rearranged, and overlaid like layers on a canvas. We saw a galaxy not just as a distant object, but as a sequence of events stitched together by gravity's hand. This wasn't the first time astronomers had seen multiple images of the same galaxy. Gravitational lensing has produced such effects before, including Einstein rings, twin images, and arcs. But with MACS J1149, the clarity, spacing, and timing of the images created an unprecedented opportunity, not only to observe a far-off galaxy in astonishing detail, but to witness how gravity could fracture a single light signal into separate moments. Each image of MACS J1149 carried the same origin, but not the same arrival time. And each delay was measurable. This gave scientists a rare gift, the ability to map not only the mass distribution of the lensing cluster but also the precise timing of how light had been delayed by different gravitational wells. The images themselves weren't evenly spaced or symmetrical, because neither the galaxy nor the lensing cluster was perfectly uniform. The arcs and duplicates we saw were lopsided, stretched, and sometimes faint, but real. And by studying them, astronomers could piece together the layout of the invisible matter that did the bending. In effect, Max J1149 became a flashlight shining through a warped lens, illuminating the invisible architecture of the universe. And it's here, in this dance of light and gravity, that something extraordinary began to unfold. Among these multiple images, in one of the arcs of light scattered across space, something happened. A new, tiny point of brilliance appeared. Not a planet. Not a star. But the final flash of a dying sun, a supernova. One that, thanks to the strange curvature of space-time, we would witness again. And again. The light from that single event had taken different roads through the cosmos. Some short, some long. Some direct, some bent nearly beyond recognition. And so, the light didn't arrive all at once. We were about to watch a star explode multiple times, from different angles, through different corridors of space-time. We were about to see the same moment, split in time. In 2014, something extraordinary appeared in one of the distorted arcs of Max J1149. Among the stretched, lensed, and time-split images of the distant galaxy, a new pinprick of light emerged, sharp, sudden, and unmistakably powerful. Astronomers around the world turned their instruments toward it. They recognized the signature almost immediately. This was not a variable star brightening slowly, nor was it an artifact of lensing alone. It was the unmistakable flash of a supernova, a star reaching the final, cataclysmic end of its life. This was the moment Supernova Refsdal entered the scene. The supernova was located in one of the multiple images of Max J1149, specifically inside a distorted spiral arm of the galaxy as seen through the gravitational lens of the intervening cluster Max J1149.5 plus 2223. Its light had traveled for more than 9 billion years, slipping and twisting through the warped web of spacetime, only to finally emerge in our field of view. But unlike other supernovae seen before, this one wasn't content to flash and fade like a cosmic firework. What made this event so breathtaking wasn't just the explosion itself, but what happened next. Soon after the initial observation, astronomers noticed something odd. The supernova appeared again, in a different part of the sky. Not in a neighboring galaxy or even in a nearby star system, but in a completely different image of the same galaxy. It was the same explosion, observed at a different location, at a different time. And then it happened again. This was not a coincidence. This was not a new supernova. It was the same event, Supernova Refsdal, its light traveling along multiple paths, each bent and delayed differently by the immense gravity of the lensing cluster between us and Max J1149. To grasp the wonder of this, consider how light travels. It always moves at the same speed, 299,792 kilometers per second, yet it doesn't always take the same amount of time to reach us, depending on the terrain it moves through. The gravitational lensing cluster acted like a maze, a complex gravitational web through which different beams of light took unique routes. Some paths were longer in distance, others passed through deeper gravitational wells, where time dilated due to stronger gravitational fields. These effects, predicted by general relativity, meant that light from the same explosion could arrive at Earth staggered in time. And it did. This wasn't just a case of seeing a supernova twice. This was seeing it multiple times, each appearance a delayed echo of the original flash, broadcast through a different channel carved by gravity itself. Supernova Refsdal was named in honor of the Norwegian astrophysicist Sjur Refsdal, who had, in 1964, theorized that such an event might someday be observable, a single supernova seen more than once due to gravitational lensing. At the time, his idea was elegant but untested. For decades, it remained a theoretical curiosity, something discussed in astrophysics circles but considered improbable. Yet here it was, 5 decades later, playing out almost exactly as he had imagined. For the first time in history, we weren't just observing a distant supernova. We were watching it unfold in pieces, like chapters in a story delivered across time. The implications were enormous. Not only did this confirm Refsdal's prediction, but it also opened up a new way to study supernovae, gravity, and the structure of the universe. With each appearance, astronomers could analyze the brightness, color, and fading pattern of the supernova. They could compare it across the different light paths, verifying that the events were indeed the same explosion. And they could use the differences in timing and angle to map the gravitational landscape of the lensing cluster in exquisite detail. The multiple sightings of Supernova Refsdal weren't just a curiosity, they were a revelation. Never before had humanity watched the same stellar death more than once through the natural machinery of the universe. This was not just the light of a dying star. This was a message sent across time through multiple channels, each shaped by invisible forces. By analyzing this event, astronomers confirmed the power of gravitational lensing not just to bend light, but to bend time. And in doing so, they took another bold step toward understanding the universe not as a fixed dome above our heads, but as a living, shifting fabric of space and time, one that could replay its own events under the right conditions. What made this all the more striking was the realization that we weren't done watching. Based on the geometry of the lensing cluster and the known behavior of light and gravitational fields, scientists made an astonishing prediction: another appearance of Supernova Refsdal was yet to come. A cosmic rerun was still inbound, light from the same explosion, still on its way through a slower, longer path. In other words, the universe hadn't finished its performance. The moment Supernova Refsdal flickered into our view not once, but multiple times, a long-standing scientific prediction leapt from theory into reality. For the first time in the history of observational astronomy, we were not merely spectators to a distant stellar death. We were watching a single supernova explode through multiple windows of time and space. This was the first ever multiply-lens supernova, and its appearance was far more than a rare event. It was a turning point. Back in 1964, Refsdal, a Norwegian astrophysicist with a profound curiosity about the behavior of light in the cosmos, theorized that if a supernova occurred in a galaxy situated behind a gravitational lens, a massive object like a galaxy cluster, the light from that explosion could be bent and redirected in such a way that it would arrive at Earth via different paths, creating the illusion of multiple supernovae when in fact they were all just staggered views of the same event. At the time, his prediction was elegant but wholly theoretical. The technology required to test such an idea didn't exist yet. We had no instruments sensitive enough, no telescopes sharp enough, no data on deep space alignments extensive enough to spot such a phenomenon even if it occurred. But Refsdal's prediction stood like a beacon in the background of astrophysical theory, an idea waiting patiently for the universe to confirm it. And confirm it, the universe did, half a century later, in dramatic fashion. Supernova Refsdal was not only the first lensed supernova seen in multiple instances, it was the exact kind of event Refsdal had described. It occurred in a spiral arm of MACS J1149, the distant galaxy already lensed and split by the massive gravitational field of the intervening galaxy cluster Max J1149.5 plus 2223. That lens had already produced multiple images of the galaxy itself, and when the star within that galaxy exploded, the light from that singular event found itself fractured along multiple gravitational pathways. Each path gave us a unique window, a slightly different perspective, a slightly different delay, a slightly different brightness. But each burst of light came from the same explosion. This wasn't just a proof of concept. It was nature itself demonstrating a deep, relativistic truth: the warping of space can create echoes of time. Astronomers immediately recognized the historical significance. The multiple images of Supernova Refsdal weren't just interesting, they were a treasure trove of information. For one, they gave scientists a way to directly test general relativity under extreme conditions, across billions of light years. Second, they offered a means to study the structure and mass distribution of the lensing cluster, especially its dark matter component, with previously unreachable precision. And third, and perhaps most profound, the appearance of the supernova across different locations and times gave researchers a unique opportunity to refine one of the biggest open questions in cosmology: the expansion rate of the universe. The moment we observed Supernova Refsdal through multiple lensing paths, it became a kind of cosmic clock. The different arrival times of its light, when combined with accurate lensing models, offered a rare way to measure the Hubble constant, the rate at which the universe is expanding. Using this supernova, we could effectively time the arrival of light waves split by billions of years and shaped by the invisible skeleton of dark matter threading through space. In many ways, this moment bridged the gap between theory and observation in the most beautiful and complete sense. Refsdal's prediction was vindicated not just in spirit, but in exquisite detail. We had not only seen a multiply-lens supernova, we had used it as a tool for measuring space-time itself. And there was something poetic in the timing. The discovery came almost exactly 50 years after Refsdal's original paper. Many of the astronomers involved in the discovery spoke of it as a tribute to a visionary thinker whose idea had waited patiently in the background of cosmology, until technology and nature conspired to bring it to life. Supernova Refsdal was named in his honor, not just because he predicted it, but because his work exemplified the very heart of science, bold theory waiting for evidence. And when that evidence arrived, it did so not with a whimper, but with cosmic thunderclaps repeated through space. The discovery was hailed as one of the most important astronomical observations of the decade. It wasn't simply a supernova. It was a gravitational experiment, a historical confirmation, and a preview of how we might one day watch the universe in layers of light and time. Multiple appearances of the same explosion, caused not by replication but by distortion. A universe that delays its own light, that reveals its own past, not through machines or simulations, but through the pure curvature of spacetime. We had seen a prediction made in the infancy of gravitational lensing theory fulfilled in real, observable light. It was groundbreaking. And it set the stage for something even more impossible, predicting the future appearance of the same supernova, light that hadn't yet arrived but was guaranteed to. There is something deeply unsettling and beautiful about watching the same moment occur again, not as a memory, not through a recording, but as if time itself has folded back upon you. In the realm of astronomy, where events are typically fixed snapshots in a linear timeline, the multiply-lens supernova Refsdal delivered something that felt almost impossible: cosmic deja vu. Due to the incredible gravitational lensing caused by the massive intervening galaxy cluster MACS J1149.5 plus 2223, the light from the single explosion of the star in the distant galaxy MACS J1149 arrived at Earth along different paths. These paths, shaped by the curvature of spacetime itself, were not equal in length or gravitational depth. Some light beams had taken a more direct route. Others had curled around the cluster, spiraled through deeper gravitational wells, and emerged only after an extended journey. Each beam, though emitted at the same moment from the exploding star, experienced its own unique voyage, some speeding ahead, others slowed by the enormous warping power of gravity. As a result, we saw the exact same supernova multiple times. Not through repetition or cyclic physics, but through the staggered arrival of light from different cosmic hallways. Each appearance was a delayed echo, and each delay had its own duration based on the intricacies of space-time distortion. The sensation was akin to seeing a lightning strike in the distance, and then hearing multiple booms of thunder, each from a slightly different direction, each separated by a measurable pause. Except instead of a few seconds of delay, the echoes of Supernova Refsdal were stretched across months, even years. Instead of traveling through clouds and atmosphere, the light was navigating the cosmic web itself, manipulated by the weight of galaxies and the invisible pull of dark matter. When astronomers detected the first instance of the supernova in 2014, it triggered a flurry of activity. Models were rapidly refined to try to understand where and when the other echoes might appear. Some of these echoes were already in archival Hubble data, faint and subtle, hiding in plain sight. Others were predicted to arrive in the near future. The feeling among astronomers was eerie and exhilarating. We knew the explosion had already happened billions of years ago, and yet we were still waiting for part of its light to arrive. This is the paradox of gravitational lensing. It turns a singular, explosive moment into a temporal mosaic. Supernova Refsdal was not exploding again and again. It had exploded once, and the universe was simply showing it to us through different mirrors, placed at different angles and depths in space-time. Each reappearance of the supernova was like turning a page in a book you've already read, but now the story is being told with a new tone, a new tempo, a new light. The same event, but with a fresh perspective. And that's not just a poetic metaphor, it's literal. Because of the lensing, each image came to us from a slightly different direction. We were seeing the same explosion from different angles, with each light path offering a subtly different geometry. It's as if we had placed cameras at various points around a dying star and set them all to deliver their footage to Earth at different times over the course of 2 years. And this cosmic déjà vu had profound scientific value. By studying the timing differences between the supernova's multiple images, astronomers were able to extract more than just wonder. They extracted data. Time delays between the images were used to refine our understanding of the lensing mass, the galaxy cluster's internal structure, the location and concentration of dark matter, and how space-time itself had been distorted. These time delays also contributed to independent estimates of the universe's expansion rate, providing a new piece of the ever-challenging puzzle known as the Hubble constant. The déjà vu was, in a sense, a natural laboratory. Scientists were watching the same experiment unfold multiple times, under slightly different conditions, with results that could be compared directly. No artificial replication was needed. Nature had provided the experimental setup, the repeated trial, and the time-stamped results. We were merely fortunate enough to witness it. Perhaps the most profound aspect of this repeated observation was what it revealed about time itself. We often think of time as linear, one event following another in a strict sequence, with no opportunity for replay. But gravitational lensing teaches us something deeper. Time, like space, can be curved, stretched, and even folded. The idea that light from the same source can reach us at different times, years apart, is not just a curiosity. It's a truth that reshapes how we think about causality and observation in the universe. And for the first time, we didn't have to imagine it, we saw it. The supernova exploded once. But we saw it again. And again. And again. Each time, the light arrived from a different direction. Each time, it was slightly different in brightness, timing, or contrast. Each time, it was unmistakably the same supernova, a point of violent beauty replayed by the cosmos. This was cosmic déjà vu in its most literal, most spectacular, most mind-bending form. The same star, the same death, the same light. Split by gravity. Delayed by space-time. Delivered in intervals. Not by design, but by alignment, an alignment so precise, so perfect, that it allowed the universe to do what no human tool had ever done before, play back the past. And what came next would take this one step further. We had seen the past. Now we would predict it. Time travel, in the classic sense of stepping into a machine and leaping forward or backward in time, remains in the realm of fiction. But in the universe's vast expanse, under the right circumstances, time itself can be experienced differently, not by breaking its laws, but by bending its path. In the case of Supernova Refsdal, the cosmos didn't send us back in time. Instead, it brought the past forward in fragments. The supernova exploded once. But due to the warping of space-time caused by an intervening galaxy cluster, the light from that single event was split into multiple paths, some longer, some shorter, resulting in a natural, physical version of time travel. To understand how this works, imagine shining a flashlight in a pitch-black canyon. If that canyon has walls at different angles and surfaces, the light beam might bounce, scatter, and reflect, reaching observers standing in various spots at different times. They all see the same original beam, but the path each ray takes determines when they see it. Now imagine those canyon walls aren't stone but gravitational distortions created by galaxies, dark matter, and space itself. The light from the supernova is the flashlight beam. The observers, us, are sitting in our corner of the universe, waiting for each version of the light to finally arrive. In a universe governed by Einstein's general relativity, space and time are woven together into a four-dimensional continuum called spacetime. Mass distorts this continuum. A massive object, such as a galaxy cluster, doesn't just pull on other objects gravitationally, it alters the very geometry of spacetime around it. This distortion is what causes light, which always travels at a constant speed in a vacuum, to bend when it passes near a massive object. But the path isn't just bent, it's reshaped in such a way that light no longer travels in a straight line, and the time it takes to reach us can vary dramatically depending on how the curvature affects each route. When the supernova in MACS J1149 erupted, its light radiated outward in all directions. Along one path, light might have passed through a relatively shallow part of the gravitational well caused by the lensing galaxy cluster. That light arrived at Earth quickly, at least quickly, in cosmological terms. Another beam of light from the same explosion might have curled around the denser core of the lensing cluster, descending into a deeper gravitational well and climbing back out before heading our way. This route was longer, and light slowed down in the curved spacetime, so it took more time to arrive. And still other rays traveled even more circuitous, gravitationally intense routes, arriving months or even a full year later. This isn't theoretical guesswork, it's measurable. Astronomers were able to observe multiple images of the supernova, each one emerging in a different location at a different time. These weren't different events. They were echoes of the same moment, delayed by light's path through curved spacetime. What this shows us is that gravity doesn't just affect matter, it affects time itself. It's helpful to picture these paths as layers in a topographical map of the universe. The deepest gravitational wells create valleys, the shallower ones create hills. Light curves through this landscape, and depending on the valley it traverses, it will be delayed more or less. The longer and more curved the path, the later the light arrives. This is what makes gravitational lensing such a unique phenomenon. It's not merely a magnifying glass in space, it's also a cosmic clock. The delay in light arrival isn't a flaw. It's a feature. It's a direct result of the shape of spacetime sculpted by the lensing mass. And by measuring these delays precisely, astronomers can do something remarkable: map the mass distribution of the lensing object in 3 dimensions, including its invisible components like dark matter. In the case of Supernova Refsdal, these delays weren't just an interesting oddity. They were evidence that time itself had been stretched. Not broken. Not looped. But divided into separate, staggered arrivals that gave us a new way to see a singular event. Each time light arrived from a new path, we saw the same supernova from a new perspective, literally and temporally. It was as if the explosion, which lasted mere days in its original location, had been extended across years by the natural warping of the cosmos. We witnessed a fleeting moment preserved, not by a telescope's lens, but by the very universe that gave birth to it. And unlike fictional time travel stories, where changing the past is the goal, this real form of time delay through gravitational lensing doesn't affect the original event. It's fixed. The supernova happened once, and its light was set on its course. But thanks to nature's manipulation of spacetime, the story unfolded for us not in a single flash, but as a staggered cascade. That's the wonder here. The universe allowed us to peer at a single moment from multiple vantage points in time and space, each shaped by gravity's invisible hand. It's time travel without paradox. Observation without interference. Replay without rewind. Supernova Refsdal didn't give us a chance to prevent a stellar death. But it gave us something perhaps even more profound, the ability to witness it as though time had slowed down, giving us a second, a third, even a fourth chance to catch the same cosmic breath. And what came next confirmed just how precise this time bending truly was. Because based on the shape of the lensing cluster and the paths light could take, astronomers made a bold declaration: they could predict the future. They could tell us when the next image of the same supernova would appear. And the universe, in its elegant silence, kept its promise. The discovery of Supernova Refsdal marked a moment where theory, observation, and cosmic choreography intersected with astonishing precision. As soon as astronomers confirmed that the bright point of light seen in 2014 was indeed a supernova and that it had been multiply-lensed by the intervening cluster MACS J1149.5 plus 2223, something extraordinary happened, not in the heavens, but here on Earth. Scientists began making predictions, not about what they might see next, but about when they would see it. They were not just studying a phenomenon, they were now participating in it. They realized that they weren't witnessing a singular event in isolation, but a staggered performance of a cosmic drama with multiple acts separated by time delays baked into the structure of the universe itself. The first confirmed image of Supernova Refsdal appeared in late 2014 in one of the mirrored arms of the galaxy MACS J1149. That brightening, a clear rise in luminosity consistent with a core-collapsed supernova, caught the attention of researchers immediately. But even more captivating was the context. The light had not simply emerged in one location. Based on existing gravitational lensing models, astronomers realized that the cluster lens, with its web of mass and curved spacetime, had already produced several prior images of that same location in the galaxy. In essence, this meant that the supernova might have already been seen in other distorted arcs of Max J1149, perhaps even years earlier, though too faint or unrecognized to have been noticed. But even more thrilling was the future. Based on models of the lensing mass distribution and the curvature of spacetime across the cluster, the team predicted that another appearance of the same supernova was still on the way. This wasn't guesswork. It was gravitational modeling at its finest. Using the known positions of the lensed galaxy images, their relative brightnesses, and their previously measured time delays, researchers fed data into sophisticated simulations of the lensing cluster. These models accounted for the distribution of visible galaxies, hot gas observed in X-ray maps, and crucially, the vast hidden scaffolding of dark matter that threads between and through it all. What they found was stunning. The models converged on a clear prediction. Somewhere in one of the other arcs, specifically in a region nicknamed the Refsdal Quad, because it showed the galaxy in a quadruple-lensed configuration, the supernova's light should reappear. Not as a coincidence. Not as a statistical possibility, but as an inevitability dictated by space-time geometry. The light from the supernova had taken multiple paths, and one of those paths, delayed by a longer route through deeper gravitational wells, had yet to arrive. The predicted reappearance was estimated to happen in late 2015, give or take a few weeks depending on the finer details of the lensing cluster's mass distribution. And so astronomers waited. Telescopes were pointed. Time slots were scheduled. Observing time on the Hubble Space Telescope was allocated for the express purpose of catching the next act of a show that had already played out billions of years ago. And then, right on cue, it happened. In December 2015, astronomers observed a new brightening in the exact region predicted by the models. There it was, Supernova Refsdal, appearing again, not as a new event, but as a rerun. A literal cosmic rerun. A flash of light emitted over 9 billion years ago had finally completed its longer journey, curling around the far side of the gravitational lens, delayed by the depths of curved spacetime. It was the same supernova, the same photons, the same death throes of a massive star, just arriving at Earth via a different route. And the timing? Astoundingly accurate. The predicted delay between the 2014 and 2015 appearances was roughly 1 year, and the actual observed delay fit well within the expected range. The models were right, not just about where the light would appear, but when. This was the first time in history that astronomers had successfully predicted the reappearance of a supernova based solely on the physics of gravitational lensing. The implications were profound. For one, it demonstrated that our understanding of gravitational lensing, including the invisible distribution of dark matter, had reached a level of maturity and precision that allowed us to treat the universe like a functioning optical device. Not only could we reconstruct the positions and masses of the lensing galaxies, but we could also use that map to forecast the future arrival of light from distant objects. This is the astronomical equivalent of predicting when a beam of light will emerge from the back end of a maze, and getting it right. It also reinforced the concept that gravitational lensing isn't just a tool for magnification, it's a tool for temporal manipulation. The universe, when curved by enough mass, becomes a delay chamber. It creates time gaps. It fractures single events into multiple moments. It allows the same story to be told again, from a different angle, and a different time. To the public, This event might seem like a curiosity, a neat astronomical trick. But to physicists and cosmologists, it was a moment that tied together strands of Einstein's theory of general relativity, the nature of spacetime, the behavior of light, and the hidden influence of dark matter. It was a proof of concept that the universe's deepest principles could not only be observed, they could be used. Moreover, it opened a door to something new, the idea of gravitationally lensed time-domain astronomy. Traditionally, astronomers observe the skies for transient events, supernovae, gamma-ray bursts, and variable stars, as they happen. But now, gravitational lensing adds a new layer, the ability to anticipate transients. To look not just for things that are currently happening, but for things that will happen again, not because they're repeating, but because their light hasn't yet finished its journey. The delay between the flashes of Supernova Refsdal, between 2014 and 2015, became a kind of cosmic heartbeat, a rhythm set by gravity's distortion of spacetime. It was a beat that confirmed the precision of our models, the power of our telescopes, and the predictive power of physics itself. And still, the echoes weren't over. The supernova's light had taken multiple paths. Some were short. Some were delayed by a year. Others, possibly, might take even longer to reach us. There was the tantalizing possibility that in decades to come, further delayed images might emerge, faint and quiet, from even longer or more complex routes through the lensing cluster. These delayed flashes are out there, already en route. Whether they arrive tomorrow or centuries from now, they are coming, silent messengers of a stellar death frozen in time. Supernova Refsdal was not just the first supernova to be seen multiple times. It was the first to be waited for. The delay between flashes wasn't a mystery, it was a message. A message from gravity, from light, from time. And from here, the story pivots. Because after catching one cosmic rerun, scientists didn't just smile in amazement, they got to work. If we could predict this supernova's reappearance, what else could we do? Could we use these delays to measure the expansion of the universe? Could we use gravity itself as a ruler for cosmic time? For as long as humanity has studied the skies, celestial events have been observed in one direction. They happen, and we witness them, often without warning, and rarely more than once. Even the most powerful telescopes in orbit and on Earth have typically been passive instruments, recording what the universe decides to show us, when it chooses to reveal it. But Supernova Refsdal shattered that convention. For the first time in recorded history, scientists did something previously unimaginable. They predicted the time and place where a specific, singular supernova would appear. Not a new explosion, but the delayed light of one that had already occurred billions of years ago. This prediction wasn't born from guesswork or intuition. It was the product of physics, mathematics, and the profound understanding of how gravity sculpts the fabric of spacetime. After the 2014 detection of Supernova Refsdal in one of the stretched and warped arcs of the lensed galaxy MACS J1149, astronomers understood that this was no ordinary sighting. Due to gravitational lensing, the supernova's light was arriving along multiple pathways. Some of those pathways had already delivered their payload. But others were still en route, twisted, delayed, and refracted by the immense gravity of the intervening galaxy cluster, Max J1149.5 plus 2223. Astronomers began building models, detailed reconstructions of the lensing cluster's mass distribution. These models had to take into account not just the visible galaxies within the cluster, but also the vast amounts of dark matter that warp spacetime invisibly. Using observations from the Hubble Space Telescope and various ground-based telescopes, they mapped the cluster's gravitational potential like cartographers surveying a mountain range made of invisible force. With each refined model, the map became more precise. Scientists could see not just where light was being bent, but by how much. And crucially, they could calculate the travel times of the different light paths taken by photons from the supernova. These weren't just theoretical curves drawn in the void, each path represented a real journey, a specific trajectory that light followed from the supernova to Earth, delayed by both distance and the time dilation effects of gravity. Among these paths, one stood out. It was longer and more warped than the others. According to the best-fitting models, the light from Supernova Refsdal along this path had not yet arrived. But it would. The delay wasn't infinite, it was measurable. And so, with extraordinary confidence, scientists predicted that sometime in late 2015, another appearance of the same supernova would emerge, not from a new event, but from light that had been traveling the long way around. The prediction was so precise that astronomers could even identify the specific region of the sky where the reappearance would occur, in one of the 4 images of the lensed galaxy known collectively as the Einstein cross. This unique configuration, caused by the near-perfect alignment of the source galaxy, the lensing cluster, and Earth, had created 4 distorted images of the same spiral arm, each at a slightly different time. And so, a global effort was launched. Observatories coordinated their efforts. Hubble scheduled dedicated observation time. Instruments were trained on that tiny region of sky, waiting. It was the astrophysical equivalent of standing on a mountaintop with a camera, knowing exactly when and where a shooting star would appear. Then, in December 2015, it happened. Right where it was predicted to appear, in the upper left arc of the lens galaxy, a new brightening occurred. The same telltale rise in luminosity. The same spectral signature. The same supernova, emerging again, a full year after its first detection. Supernova Refsdal had returned. It wasn't just a stunning scientific achievement, it was a historic first. Never before had a specific transient event in the distant universe been predicted with such accuracy, based solely on gravitational lensing models. It was as if we had decoded a secret schedule embedded in the curvature of the cosmos. The success of this prediction opened the floodgates of possibility. For the first time, gravitational lensing had proven itself not just as a lens or a magnifier, but as a predictive tool. It was a way to forecast when ancient light, already emitted, would arrive at Earth. This changed the nature of observational astronomy itself, from a passive endeavor to one where certain events could be scheduled like eclipses or planetary alignments. And this predictive power was more than just a curiosity. It validated our understanding of gravitational physics on truly cosmic scales. It confirmed that our models of dark matter distribution were accurate enough to make time-sensitive predictions. It gave us confidence in using these models to answer other big questions, like refining the Hubble constant, or even searching for other gravitationally lensed supernovae or transients in similarly lensed galaxies. The ability to predict a supernova's delayed arrival was a triumph of both theory and observation. It showed that the universe's most violent moments could be mapped and forecast using nothing more than the rules of gravity and light. And in doing so, it redefined the very idea of watching the past unfold, not just by observing ancient light, but by anticipating its arrival. This success wasn't just the fulfillment of Sir Refsdal's original prediction from 1964. It was the evolution of his vision into a fully fledged method for exploring time itself. The cosmos had delivered not just an echo, but a calendar. And we, for the first time, knew exactly when to listen. When Albert Einstein published his general theory of relativity in 1915, he proposed something radically different from Newton's view of gravity. No longer was gravity simply a force acting at a distance between masses. Instead, it was the warping of spacetime itself. Massive objects didn't pull on others. They bent the very fabric of space and time, and other objects merely followed the curves. This elegant model predicted a strange and subtle consequence. Even light, massless and fast, should bend when passing near a massive object. A prediction considered outrageous at the time. That prediction was first confirmed in 1919 during a solar eclipse, when starlight passing near the Sun was observed to shift slightly in position, just as Einstein had forecast. That result made him world famous. But that was merely the beginning. Over the decades, general relativity has been tested in a number of increasingly precise ways, through time dilation measured by satellites, by observing the orbits of Mercury and pulsars, by detecting gravitational waves. Yet one of the most breathtaking confirmations came not from our solar system, not from a laboratory, but from a galaxy so distant its light had traveled 9.3 billion years to reach us. That confirmation came through Supernova Refsdal. When astronomers observed the same supernova appear in different places and at different times, they weren't just watching a celestial magic trick, they were witnessing general relativity in full, majestic operation on the largest stage imaginable. Light from the same explosion had bent around a massive foreground galaxy cluster, MACS J1149.5 plus 2223, and arrived at Earth through different gravitationally curved pathways. This light did not merely follow a straight route through flat, empty space. It obeyed the curvature sculpted by the mass of the cluster, a curvature predicted exactly by Einstein's equations. The time delays between the supernova's appearances were not just quirks of geometry. They were physical consequences of how gravity slows time in the vicinity of mass. The more massive the object, and the deeper the gravitational potential well it creates, the more time dilates. Photons traveling through deeper curves in spacetime take longer to emerge, not because they're moving slower in speed, but because time itself is being stretched along the path. Einstein had described this very phenomenon a century earlier using the language of curved geodesics, the paths that light and matter follow when space and time are warped. But for all the success of general relativity in nearby systems, Supernova Refsdal gave us a view of its accuracy over truly cosmological distances. This wasn't a theory being tested around the Sun or within a star cluster. It was being tested across billions of light years, involving the complex interplay of multiple gravitational lenses, curved space, and delayed light. And what's more, it passed the test with astonishing precision. The models used to predict the reappearance of the supernova in 2015, based entirely on Einstein's theory, were not just approximate. They nailed the location, the brightness, and the timing of the delayed image within weeks of its actual arrival. These models incorporated the equations of general relativity to simulate how spacetime would be curved by the cluster's mass, and how photons from a point source, in this case, the exploding star, would travel through that warped terrain. It's one thing for a theory to explain something we observe. It's another for it to predict an event in spacetime with such precision that we can plan for it, schedule telescope time, assign coordinates, and then witness the cosmos act exactly as predicted. That's not just validation. That's mastery. But the implications go even deeper. The bending and delaying of light allowed by general relativity also enabled astronomers to probe the otherwise invisible components of the lensing cluster, especially dark matter. Since we can't see dark matter directly, we infer its presence by how it bends light from background objects. And in the case of MACS J1149.5 plus 2223, the dark matter wasn't just bending space, it was delaying time. The delay intervals between the different supernova images let researchers reverse engineer the cluster's mass distribution, effectively using Einstein's theory to reveal what would otherwise remain hidden. This is gravitational lensing at its finest, a telescope made of gravity itself, sharpening our vision not just spatially but temporally. And the theory that made sense of it all, across 9.3 billion light-years, across warped galaxies, and over delayed cosmic signals, was Einstein's general relativity. Supernova Refsdal thus became more than just a distant dying star. It became a cosmic laboratory, a proof point that the equations Einstein penned in an era before even television had the power to describe and predict the universe in ways even he may never have imagined. And remarkably, they didn't just work, they worked precisely. No modification was needed. No glaring gaps appeared. No contradiction challenged the theory's predictions. General relativity held firm. This success also had philosophical weight. It reminded us that the universe is not just a collection of random, disconnected events. It's a system governed by rules, elegant, abstract, yet concrete rules, that allow us not only to understand what has happened, but also what will. In watching Supernova Refsdal appear repeatedly, staggered by the gravity of a galaxy cluster billions of light-years away, we were watching Einstein's vision of reality unfold, curved space, slowed time, and light tracing the edges of gravity's invisible contours. And with every flicker of that distant explosion, the theory gained not just confidence but relevance. It showed us that our understanding of gravity is not a local fluke or a near-Earth convenience. It scales. It operates with majestic consistency, from the bending of starlight in our own solar system to the echoing collapse of a star more than halfway across the observable universe. We had not merely seen a supernova, we had seen space and time bend. We had seen a century-old theory whisper across the cosmos. Yes, I still work. And I still have more to show you. The universe is vast beyond comprehension, and as we peer deeper into its depths, our vision is constantly challenged by the faintness of distant objects. Galaxies that formed billions of years ago emit light that must traverse the ever-expanding cosmos to reach us, growing dimmer and redder along the way. For the most distant galaxies, those formed in the early epochs of the universe, this light is so stretched, so faint, that even our most advanced telescopes would normally be blind to them. And yet, remarkably, we've found a way to see farther and deeper, not by building larger lenses or mirrors, but by using the universe's own machinery. We call it gravitational lensing. And in the case of MACS J1149 and Supernova Refsdal, nature itself became our telescope. Gravitational lensing is not merely a way to bend light, it's a way to magnify it. When a massive object like a galaxy cluster sits directly between us and a more distant galaxy, the immense gravity of that cluster warps spacetime in such a way that it acts like a lens. It bends, distorts, and focuses the light of the background galaxy toward us. In some configurations, it creates multiple images. In others, it stretches the background object into long arcs or rings. But in almost all cases, it also amplifies the light. This natural magnification is what allowed us to see MACS J1149 in such detail in the first place. Without the lensing effect of the cluster MACS J1149.5 plus 2223, the distant galaxy hiding behind it, located a staggering 9.3 billion light-years away, might have been nothing more than a whisper of photons against the blackness of space. But because of the alignment between our line of sight, the galaxy cluster, and the distant galaxy, the latter's light was not only bent toward us, it was brightened. Like placing a candle behind a magnifying glass, the faint glimmer of ancient starlight was magnified enough for Hubble to detect it. In this way, gravitational lensing acts as nature's telescope, one that doesn't require lenses or mirrors, but uses mass itself to alter the flow of light. And this natural telescope is not limited by human construction or atmospheric interference. It spans millions of light-years. It operates on the most colossal scales. And it reveals parts of the cosmos that would otherwise be beyond the reach of even the most ambitious engineering. This is precisely why regions like MACS J1149.5 plus 2223 were chosen as part of programs like the Hubble Frontier Fields, a project specifically designed to peer deeper into the universe by using gravitational lensing to study some of the most distant galaxies ever observed. Astronomers intentionally target massive galaxy clusters, not only for what they contain, but for what they reveal behind them. These clusters become cosmic lenses, uncovering galaxies from the early universe, galaxies that formed when the cosmos was only a few billion years old. MACS J1149 is a perfect example. Thanks to lensing, we've been able to observe its structure, detect individual star-forming regions, and witness the supernova that would become Refsdal. Without lensing, this galaxy would be too faint to resolve, its light too diffuse and redshifted to distinguish from the cosmic background. But with the lensing effect, we gain not only visibility, but clarity. We can study this ancient galaxy in a level of detail comparable to galaxies much closer to home. In the case of Supernova Refsdal, lensing didn't just make the host galaxy visible, it made the supernova itself observable. A stellar explosion that occurred billions of years ago in a faint, far-off spiral arm was magnified enough to be seen by Hubble, not once, but multiple times. The lensing effect served as both spotlight and projector, lifting the explosion out of obscurity and placing it on a grand cosmic stage. And this magnification has broader implications. It means we can study the early universe with greater precision. We can examine galaxies that would otherwise be inaccessible, small, primitive galaxies forming stars at the dawn of time. We can investigate how galaxies grow, merge, and evolve, and how the first stars and black holes shaped the cosmos. But perhaps most powerfully, it reminds us that the universe is filled with tools hidden in plain sight. Instead of reaching farther with brute force, building ever bigger observatories, we can also look for alignments, for the natural optical systems embedded in the structure of space itself. A massive cluster of galaxies, formed through eons of gravitational collapse, becomes an instrument of focus. Space, warped by mass, becomes a lens. Nature provides the infrastructure. We merely have to find it and point our telescopes in the right direction. In fact, gravitational lensing is now a cornerstone of modern astronomy. We use it to locate dark matter by analyzing how light is bent around invisible clumps. We use it to study exoplanets as they magnify stars they pass in front of. And in rare cases like MACS J1149, we use it to catch and rewatch a stellar explosion that would otherwise have passed in silence. This transformation, of a galaxy cluster into a magnifying glass, of mass into a lens, of gravity into optics, is one of the most elegant examples of physics at work. It shows that even phenomena as intangible as space-time curvature can become practical tools. Tools that extend our vision. Tools that let us see what the naked eye, even the unaided telescope, never could. Max J1149.5 plus 2223 is now not just an object of study, but a collaborator. A partner in our effort to understand the earliest epochs of the universe. Its lensing effect gave us the galaxy behind it, the supernova within it, and a new window into the very nature of time and light. Thanks to nature's telescope, the faintest echoes of the distant universe grow loud enough to hear. When we gaze at Max J1149, we aren't just looking across space, we're looking deep into time. The light from this distant galaxy began its journey toward us over 9.3 billion years ago, during a vastly different cosmic era. At that time, the universe was still a young and restless place, barely a third of its current age. The cosmos had cooled enough to allow galaxies to form, but it was still buzzing with star birth, collisions, and the chaotic interplay of matter and gravity. In seeing Max J1149 today, we are essentially peering through a natural time machine, catching a glimpse of what the universe looked like when it was less than 5 billion years old. To put that in perspective, Earth itself didn't even exist yet. Our Sun wouldn't form for another 4.5 billion years. The Milky Way's spiral arms were still assembling. The cosmic microwave background, leftover radiation from the Big Bang, was still relatively fresh, and the large-scale structure of the universe, with its filaments of galaxies and dark matter, was still taking shape. It was a time of furious construction across the cosmos. Max J1149 gives us a frozen snapshot of that formative epoch. The galaxy's light, stretched and magnified by the intervening lensing cluster, reveals to us not only its structure, but also its stage in cosmic evolution. When astronomers observe this galaxy, they see signs of active star formation, regions glowing with newborn stars, possibly triggered by galactic mergers or internal gravitational instabilities. Its shape appears disrupted and lopsided in some images, suggesting that it may be interacting with neighboring galaxies, or is itself undergoing a process of transformation common in the early universe. This is important, because the universe we live in today, full of majestic spirals like the Milky Way and massive ellipticals like M87, did not always look this way. Early galaxies were smaller, more irregular, more chaotic. They merged frequently, collided violently, and evolved rapidly. By studying Max J1149, we are effectively watching the adolescence of galactic life, the rough and rowdy years that shape the smoother, more mature forms we see in the nearby universe. But how exactly do we see something that far back in time? The answer lies in light itself. Light travels at a finite speed, 299,792 kilometers per second. That means when we observe distant objects, we aren't seeing them as they are now, but as they were when the light left them. The farther away the object, the older the light. For Max J1149, that light has been traveling across the universe since before our solar system existed. And because the universe has expanded over those 9.3 billion years, that light has been stretched, its wavelength elongated from the visible spectrum toward the infrared, a phenomenon known as redshift. The higher the redshift, the older the light. MACS J1149 has a redshift of approximately z equals 1.5, which corresponds to a time when the universe was just entering its midlife crisis. Star formation across the cosmos was near its peak. Supermassive black holes were actively feeding in the centers of galaxies. Quasars lit up the skies, and the chemical elements forged in the first generations of stars were spreading outward, enriching future stars and planets with carbon, oxygen, and iron. In this way, galaxies like MACS J1149 aren't just relics. They are active records of the universe's evolution. They help astronomers understand how structure formed and transformed across cosmic history. By examining their light, scientists can reconstruct the growth of stars, the assembly of galaxies, and the influence of dark matter over time. Each lensed arc, each magnified spiral arm, becomes a frame in the movie of cosmic development. The magnification provided by gravitational lensing is what makes this study possible. Without it, MACS J1149 would likely be too faint to resolve in detail. But with the added boost, astronomers can observe not just the galaxy's overall brightness, but its individual components, clumps of stars, bursts of light, and even the brilliant flare of Supernova Refsdal. That supernova itself adds another layer to the story. It tells us that massive stars were already being born and dying in that distant galaxy, that the stellar life cycle was already in full swing. The presence of such a supernova shows us that the universe, even in its youth, had matured enough to allow the full cycle of stellar evolution, from formation to collapse, to unfold. And these observations have a ripple effect across science. By analyzing galaxies like MACS J1149 at different redshifts, astronomers can chart the star formation history of the universe. They can determine when the first stars formed, how galaxies grew larger, and how structures like clusters and superclusters assembled over time. They can test cosmological models against real data, refining parameters like the rate of expansion, the Hubble constant, and the density of dark matter. MACS J1149 is more than just a beautiful lensed galaxy. It is a time capsule. It is a window into an era of intense cosmic activity, when the scaffolding of today's universe was still under construction. Its distorted image, made clearer by the lensing cluster, serves not only as a confirmation of physics, but as a revelation of history. We often think of time travel as the domain of science fiction. But every image of a distant galaxy is, in fact, a voyage into the past. We don't need to build a machine to travel through time. We simply need to open our eyes to the light that has been journeying toward us for billions of years. In MACS J1149, that journey is amplified, elongated, and mirrored by gravitational lensing. The galaxy appears not once but many times, like an echo frozen in space-time. And with each arc, with each flicker of ancient light, we learn more about who we are and where we came from. Because in looking out, truly far out, we are also looking back. And what we see, glowing softly through the warped lens of a galaxy cluster, is our cosmic origin story unfolding in real time. One of the most profound yet elusive components of our universe is dark matter. It doesn't emit, absorb, or reflect light, making it invisible to telescopes and undetectable through conventional means. And yet, it comprises the majority of matter in the cosmos, about 5 times more abundant than ordinary, visible matter. If we cannot see it, how do we know it's there? And more intriguingly, how can we map something that, by its very nature, refuses to reveal itself? The answer lies in the behavior of light. Specifically in the way light from distant galaxies, like MACS J1149, is distorted by the gravitational influence of foreground galaxy clusters. These distortions act as subtle fingerprints of invisible mass, allowing us to reconstruct not only where dark matter is, but how it is distributed across the vast scaffolding of the universe. In the case of MACS J1149.5 plus 2223, the galaxy cluster that sits between Earth and the distant galaxy MACS J1149, gravitational lensing reveals far more than just magnified images. It shows us how much mass is present in the cluster, where that mass lies, and how it warps the fabric of space-time. The distorted arcs, multiple images, and delayed flashes of light from Supernova Refsdal are not random. They are a direct consequence of how matter, visible and invisible, is arranged within the lensing cluster. By carefully measuring these distortions, astronomers can reverse engineer the gravitational lens. This process, often called mass mapping, uses the bent trajectories of photons from background sources to trace out the gravitational potential of the foreground cluster. And here's the key. The visible galaxies in MACS J1149.5 plus 2223 account for only a small fraction of the lensing power. The rest, often the majority, comes from dark matter. This means the arcs and smeared images of the lens background galaxy are not merely curious phenomena, they are diagnostic tools. Each stretched spiral, each duplicated supernova, each subtle shearing of a background galaxy tells us something about the structure of the dark matter in the cluster. The brighter and more distorted the image, the stronger the lensing effect, and the more mass, visible or dark, must be present in that region. Astronomers use this information to create dark matter maps. These are not speculative drawings, but data-driven reconstructions that show where dark matter is likely to reside, based on the observed lensing features. These maps often reveal surprising truths. Dark matter is not evenly distributed. It clumps in clusters, forming halos around galaxies and filaments connecting them across intergalactic space. In lensing clusters like MACS J1149.5 plus 2223, dark matter forms a complex, layered web that cannot be explained by visible galaxies alone. One of the most powerful aspects of this method is that it works across vast distances. The more distorted the background image, the stronger the lensing signal, and the clearer the dark matter structure becomes. In fact, gravitational lensing is currently one of the only tools we have to directly infer the presence and distribution of dark matter on cosmic scales. In the case of Supernova Refsdal, the lensing cluster's mass map had to be precise. Predicting when and where the supernova would reappear required knowing not only the visible matter, galaxies, stars, and hot gas, but also the invisible components that influence the light paths. It was only by including dark matter in the gravitational models that scientists could forecast the supernova's delayed image with such uncanny accuracy. And here lies a deeper revelation. The success of that prediction didn't just confirm the phenomenon of gravitational lensing. It validated the reality of dark matter. If dark matter did not exist, if the cluster's lensing power came only from what we could see, the models would have failed. The light would not have bent as strongly. The delay would not have matched. The predicted reappearance of the supernova would not have aligned with observation. But it did. Dark matter, though invisible, left behind a trail, a fingerprint in light. It sculpted the images of MACS J1149 into mirrored arcs. It delayed photons by years, rerouting them through deeper wells of spacetime. It etched its presence into the very structure of the lens, and by studying that structure, astronomers were able to lift the veil and glimpse the shape of the unseen. What's more, by mapping dark matter in multiple galaxy clusters, astronomers have begun to assemble a picture of its large-scale behavior. It doesn't interact with light or normal matter in familiar ways. It doesn't clump like stars or radiate heat like gas. Instead, it behaves like a silent scaffold, shaping the gravitational backbone of the universe. Its presence influences galaxy formation, cosmic expansion, and even the fate of the cosmos itself. The lensing cluster MACS J1149.5 plus 2223 thus becomes more than a cosmic magnifier. It is a scientific instrument, a natural laboratory for studying the invisible. Every arc of light, every duplicate galaxy image, every delayed flicker of supernova light adds to our understanding of the dark universe. These aren't just beautiful distortions, they are coded messages, encrypted by gravity and decoded by physics. In using gravitational lenses to map dark matter, we are engaging in one of the most profound detective stories in science. We are finding the unseen, tracing the intangible, measuring the unmeasurable. And in doing so, we are peeling back the curtain on the 85% of matter that has shaped everything we know, yet remains one of the greatest mysteries of modern cosmology. MACS J1149 helped show that dark matter is not just a mathematical placeholder. It is real. It is present. And with every new lensed galaxy, every distorted supernova, And every echo of ancient light, we are bringing its hidden architecture into the light. When we look at the night sky, we're used to seeing stars and galaxies as singular points or extended shapes, each in its own position, fixed and clean, as though drawn precisely on the canvas of space. But gravitational lensing forces us to rethink that simplicity. In the presence of an enormous gravitational field, like the one generated by the galaxy cluster MACS J1149.5 plus 2223, light behaves in ways that defy intuition. It splits. It duplicates. It curves around invisible masses. And in the case of MACS J1149, the result was extraordinary, not one view of the background galaxy, but multiple. Several images of the same galaxy, appearing as glowing arcs, each arriving from different paths, each representing the galaxy at slightly different moments in time. This isn't a trick of the telescope or an illusion in the optics. It's a natural phenomenon predicted by Einstein's general theory of relativity. The immense mass of the foreground cluster warps the spacetime between us and the background galaxy MACS J1149, acting like a cosmic lens. As light from the background galaxy travels toward Earth, it encounters the warped spacetime around the cluster and is deflected. Depending on the path that light takes, whether it skirts closely to the cluster's core, glides by a subclump of dark matter, or flows through a more open channel, it arrives at Earth at a different angle, and with a different time delay. To our telescopes, this creates multiple, often stretched and smeared, images of the same galaxy. These images can take on dramatic forms, rings, arcs, mirrored spirals, or sometimes even near-identical copies scattered across the sky. Each one is the same source, but distorted by the lensing cluster's complex gravitational fingerprint. They appear to surround the lens like pieces of a puzzle, sometimes overlapping, sometimes forming symmetric shapes that echo one another across the lens plane. MACS J1149.5 plus 2223 created such a puzzle. It turned a single distant galaxy into a set of elongated arcs, each one a piece of a larger story. These arcs were not just replicas in space, they were replicas in time. Because of the different paths and gravitational wells the light had to pass through, each image represented the galaxy as it appeared at a slightly different moment in the past. This is where the story turns from beautiful to profound. Each image was effectively a time-stamped photograph, shaped by both space and time. And this was never more apparent than with the supernova known as Refsdal. As it exploded in the host galaxy, its light rippled outward, eventually reaching Earth, but not all at once. One path brought it to us in 2014. Another, slightly longer and more curved, delivered it again in 2015. Others had arrived earlier, though they weren't detected at the time. And thanks to careful modeling of the lens geometry, scientists were able to reconstruct where and when each appearance would occur. These different routes through spacetime allowed us to witness the same explosion more than once. Not through simulation, not through archival data, but live, in the cosmos itself. This effect, the splitting of a galaxy's image into several versions, each a distorted echo, is unique to gravitational lensing. It offers more than just visual spectacle. It provides a rare opportunity to study a galaxy, or an event within it, from multiple lines of sight. Each path taken by the light offers a slightly different perspective, a different magnification, or a different time delay. By comparing these differences, astronomers can infer details about the galaxy's structure, its star-forming regions, its motion, and its internal brightness variations, sometimes even catching fluctuations that might otherwise go unnoticed. Furthermore, these multiple images are essential for understanding the gravitational lens itself. They act like tracers, revealing how mass, including dark matter, is distributed within the lensing cluster. If a background galaxy appears in 3 places instead of 4, or if one image is fainter than expected, this hints at the presence of unseen mass substructures, possibly dense pockets of dark matter or even rogue black holes hiding in the cluster's outskirts. In some cases, the geometry of the lens and source is so perfectly aligned that the galaxy is not merely doubled or quadrupled, it is smeared into a near-complete circle known as an Einstein ring. Though MACS J1149 didn't form a complete ring, its arcs and mirrored structures showed clear signs of strong lensing. These arcs not only magnified the galaxy's features but also provided an elegant demonstration of space-time curvature at work. Multiple images of a single galaxy also underscore a more abstract idea, that the universe doesn't always offer one version of reality. In regions warped by gravity, we get layers of perspective, each governed by the invisible scaffolding of mass that shapes the cosmos. It's as if the universe permits us a second look, or a third, or a fourth, if only we happen to be standing in the right spot. In the case of MACS J1149, we were. And thanks to that alignment, we've not only witnessed a galaxy from a time when the universe was young, but we've seen it echo through space like a chorus of ancient light, scattered across the sky. These arcs are more than reflections. They're artifacts of time and space intersecting. Each one tells the same story, but from a different chapter. And as we learn to read them, we peel back layers of a cosmos that is not only vast but rich with overlapping timelines, each frozen in photons that have traveled for eons to reach us. Supernova Refsdal wasn't just a cosmic spectacle, it was a rare opportunity to do something never before possible in the history of astronomy, to reconstruct a timeline of a single stellar explosion from multiple perspectives, each arriving at Earth via different routes through space and time. What made this feat so extraordinary wasn't just the event itself, a star's final, fiery breath, but the way its light had been divided, bent, delayed, and delivered in fragments by the gravitational lens formed by the intervening galaxy cluster MACS J1149.5 plus 2223. This wasn't a single flash caught once in the sky. It was an astronomical mosaic, a timeline built from light that took divergent paths across the universe. Imagine a star exploding 9 billion years ago in a faraway galaxy. Its light radiates outward in all directions. Some of that light travels the shortest, most direct route to Earth, but that path passes through a massive gravitational lens, the cluster MACS J1149.5 plus 2223. As the light nears the cluster, it's split into multiple beams, each one deflected along a different curve of spacetime, depending on where and how it interacts with the gravity wells created by galaxies and dark matter within the cluster. These different beams, now separated in both angle and time, eventually converge at Earth, but not all at once. Some arrive early. Some arrive late. Some are brighter, others dimmer, depending on how their paths compressed or stretched the light. And each of these paths gives astronomers a slightly different version of the same event, like multiple security cameras capturing a scene from different corners of a building, each with a different timestamp. That's exactly what astronomers had with Supernova Refsdal. The first clear detection of the supernova came in 2014, when the Hubble Space Telescope observed 4 separate images of the same supernova forming an almost perfect cross, a formation known as an Einstein cross, in one of the lens versions of the galaxy. These 4 images, caused by the supernova's light being split by a single elliptical galaxy within the cluster, arrived almost simultaneously due to the near symmetry of the gravitational field in that region. Each one showed the same explosion, separated by only days or weeks. It was a spectacular sight, but even more tantalizing was what it implied. If 4 images had appeared there, could more still be on the way? The answer was yes. Using sophisticated gravitational lensing models, scientists predicted that another image of the same supernova should appear in a different part of the sky, a different lens version of the galaxy, within about a year. That prediction came true in 2015, when Hubble observed the supernova reappearing, just as expected. It was a moment of scientific triumph, but also the beginning of something deeper, the process of building a complete timeline of the explosion by stitching together each arrival of light, one delayed path at a time. This reconstruction wasn't as simple as lining up a series of photographs. Each image of the supernova had passed through different gravitational terrain. Some were highly magnified, revealing more detail about the explosion's peak brightness and decline. Others were fainter, revealing the structure of the surrounding spiral arm or changes in the background galaxy's brightness. The timing of each arrival gave astronomers a way to measure how long each photon had taken to reach us, information that could be used to refine models of both the cluster's mass and the shape of spacetime around it. Astronomers carefully analyzed the light curves, the rise and fall of brightness over time, for each appearance of the supernova. By comparing these curves, they were able to create a composite profile of the entire event. In effect, they were able to rewind and replay the supernova from multiple angles. One image might show the early rise in brightness, another the peak luminosity, another the slow fade. And because some images arrived a year after others, the team could not only measure how the light changed over time but do so in a way that was immune to observational gaps. If clouds blocked a telescope one night, or if a particular detail was missed in one appearance, another light path might still carry that missing information. This timeline, assembled from different light paths, provided an unprecedented level of detail for a supernova so far away. Normally, observing a single supernova in a distant galaxy provides just one chance to capture the event as it unfolds. But gravitational lensing, in this case, turned that one chance into multiple. It created a time-delayed archive of the explosion, and astronomers took full advantage. The implications went far beyond the supernova itself. By comparing the delays between the different images, scientists could test and refine their gravitational lensing models. These models are sensitive to the mass distribution within the cluster, particularly to dark matter. If a model predicted a supernova reappearance too early or too late, it meant the mass distribution needed adjustment. In this way, the supernova timeline became a calibration tool, one that helped astronomers map the invisible structure of the lensing cluster with far greater precision. But perhaps most remarkably, this entire process transformed our understanding of what it means to observe a cosmic event. It proved that under the right circumstances, the universe itself can record its own history, not in ink or film, but in photons traveling along varied paths through warped spacetime. The sky, when properly interpreted, becomes a memory bank of ancient light, capable of replaying its most dramatic moments. The Supernova Refsdal timeline is now a model for future research. It has shown that when light is bent and delayed in just the right way, we can reconstruct the life and death of stars with a fidelity that was once unimaginable for galaxies so distant. And as more gravitationally lensed supernovae are discovered, astronomers will build more of these timelines, unlocking deeper insights into stellar evolution, galaxy formation, and the hidden geometry of the universe. In the folds of warped space, light can echo. And when we gather those echoes and piece them together, we don't just witness history, we rebuild it. One of the greatest challenges in modern cosmology is answering a deceptively simple question: how fast is the universe expanding? This rate of expansion, known as the Hubble constant, tells us how quickly galaxies are receding from one another, and it holds the key to understanding the age, size, and fate of the universe. Yet despite decades of effort and increasingly precise instruments, astronomers have found themselves facing a strange and stubborn tension. Different methods give different results. This Hubble tension, as it's often called, may point to unknown physics. And surprisingly, the tangled arcs of light from a supernova billions of light years away, bent by a galaxy cluster into repeated images, might offer one of the clearest ways to help resolve it. This is where Supernova Refsdal becomes more than just a beautiful anomaly or proof of gravitational lensing. It becomes a cosmic ruler. When light from a distant event like a supernova travels through a gravitational lens, the different paths it takes aren't all equal in length. Some are longer, some shorter. But more importantly, they aren't just curved differently, they also pass through regions of different gravitational potential. According to Einstein's general relativity, both distance and gravity affect the travel time of light. So when multiple images of a supernova arrive at different times, those delays aren't random. They encode precise information about how the universe is expanding. Here's how that works. By knowing the geometry of the lens, the mass distribution of the intervening cluster, the positions of the multiple images, and the time delays between them, astronomers can model the overall shape of spacetime between us and the distant galaxy. And once they've done that, they can extract a value for the Hubble constant that best fits the observed data. The process is a bit like triangulating a mountain's height using shadows. If you know the angle of the light, the position of the shadow, and the curvature of the ground, you can calculate the height precisely. In this case, the mountain is the space between galaxies, the shadow is the delayed light from the supernova, and the angle of light is shaped by the underlying cosmic expansion rate. This method, known as time delay cosmography, has been applied before, but mostly using quasars, which are active, variable galaxies that flicker over time and can be multiply-lensed. Supernova Refsdal was the first time a multiply-image supernova was used this way. Unlike quasars, supernovae have well-understood light curves. Their brightness over time follows a predictable pattern, rising, peaking, and fading in a way that can be precisely modeled. This makes it easier to measure the exact delay between different images. And since Type II supernovae like Refsdal are relatively consistent in their behavior, astronomers can use them as standardizable candles, meaning their intrinsic brightness can be inferred, further refining the measurements. With Supernova Refsdal, scientists measured the time delays between its multiple appearances, from the initial 2014 detection to the predicted 2015 reappearance, and used these delays, combined with the mass map of MACS J1149.5 plus 2223, to calculate a value for the Hubble constant. The result? A measurement that was consistent with other gravitational lensing-based methods, but intriguingly different from those obtained via the cosmic microwave background (CMB) data from the early universe. This discrepancy adds weight to the ongoing debate in cosmology. Why do local measurements of the Hubble constant, like those using Cepheid variables or supernovae, yield a higher value, 73, 74 km/s/mpc, while early universe measurements using the CMB and Planck satellite data suggest a lower value, 67, 68 km/s/mpc? Is this difference due to hidden systematic errors? Or is it telling us something new about the universe itself? Perhaps the rate of expansion is not constant, or perhaps new physics, unknown forms of energy or interactions, are at play. Supernova Refsdal's role in this is subtle but powerful. Because it offers a completely independent way to measure the Hubble constant, free from the assumptions used in other methods, it serves as a critical check on both ends of the debate. As more lensed supernovae are discovered and time delays are precisely measured, we'll be able to expand this technique, reduce uncertainties, and refine our cosmic ruler. And this method has another unique advantage: it's rooted in direct observation. While early universe methods rely on modeling the conditions shortly after the Big Bang, and local methods depend on a ladder of distance indicators, gravitational lensing and time delays are direct consequences of the physics of light in curved spacetime. They don't require us to calibrate intermediate steps or assume the properties of nearby galaxies. The light from a supernova, bent and delayed by a galaxy cluster, tells us what it experienced, nothing more, nothing less. In the case of MACS J1149 and Supernova Refsdal, this simplicity is what makes the measurement so compelling. It's the cosmos using its own mechanics, gravity, light, time, to give us answers. Imagine that. A star explodes billions of years ago. Its light, torn and stretched by gravity, takes multiple paths to reach us. We catch it once, then again, and again. And from those flickers, mere specks in our telescopes, we learn how fast the universe is running away from itself. In a sense, the universe is measuring itself for us. That's the beauty of using gravitationally lensed supernovae for cosmology. They are both events and instruments. They are messengers, delivering not just stories of stellar death, but the shape and speed of the universe itself. As more time delay events like Refsdal are discovered, and they will be, especially with upcoming telescopes like the Vera C. Rubin Observatory and the James Webb Space Telescope, the precision of this method will grow. We may yet close the gap in the Hubble tension, or discover something altogether unexpected in the process. From the distant arcs of MACS J1149, across the warped fabric of spacetime, through the exploding light of a dying star, we inch closer to understanding how everything moves apart, and why. In 1964, a Norwegian astrophysicist named Sjur Refsdal proposed an idea so ahead of its time that the technology to prove it wouldn't exist for decades. He imagined a scenario in which a supernova, an exploding star, could appear more than once in the sky, not because it exploded multiple times, but because its light took multiple paths around a massive gravitational lens. If such a supernova could be observed through a galaxy cluster, its multiple images would arrive at different times due to the varying lengths and gravitational depths of the paths taken by the light. Refsdal's insight was both elegant and profound. By measuring these time delays, one could not only confirm general relativity but also use them to probe the expansion rate of the universe. It was, essentially, a prediction of cosmic deja vu, a theoretical blueprint for time-traveling light. At the time, Refsdal's theory was an intellectual curiosity, something relegated to the fringes of cosmology textbooks. The tools needed to test his idea, a space telescope with extreme sensitivity, long-term sky monitoring, precise modeling of gravitational lenses, and the discovery of just the right cosmic alignment, were all out of reach in the mid-20th century. But the idea lingered, a brilliant spark waiting for its moment. That moment came half a century later, in 2014, with the discovery of Supernova Refsdal and the lensed galaxy MACS J1149. For the first time in astronomical history, the phenomenon Refsdal had predicted was observed in the wild. A star exploded 9.3 billion light-years away, and its light, bent by the immense gravitational field of the MACS J1149.5 plus 2223 cluster, split into several distinct images. Some arrived together, forming a stunning Einstein cross around a foreground galaxy. One arrived years earlier and had been missed. Another was predicted to arrive in the future. The universe, through a carefully warped sheet of space-time, had granted us a natural replay of a cosmic event. And with it, the opportunity to test the very predictions Refsdal had made. The naming of the supernova after him wasn't just a tribute, it was an acknowledgement that his theory had finally leapt from chalkboard to cosmos. This was more than coincidence. It was the scientific process at its most poetic, a theoretical concept drifting through decades of scientific progress, waiting for the sky to align just right, and then being proven not by design, but by nature itself. Refsdal's theory had implications that went well beyond astronomy. It linked the abstract mathematics of general relativity with tangible, observable phenomena. It showed that light is not just a beam, it is a time capsule, one that can be split, delayed, and recombined by the geometry of the universe. And it offered a new way to measure cosmic distances in time, not by rulers or redshift ladders, but by the ticking of light itself. With the Refsdal supernova, scientists didn't just verify that such time-delayed light echoes could happen, they used them. They tested lensing models, refined measurements of the Hubble constant, and even predicted a future appearance of the supernova, which was successfully observed in 2015, just as the models suggested. That predictive power, that ability to say, "The light from this explosion will reappear here, on this date," is a scientific marvel. It's not unlike forecasting the position of a planet during a solar eclipse, except in this case, we're forecasting the reappearance of a star's death throes, billions of years after the fact. Refsdal, who passed away in 2009, never lived to see his theory confirmed by observation. But his legacy was fulfilled in a way few theorists ever experience. The universe conspired to put on a show he had scripted half a century earlier. In doing so, it gave modern cosmology one of its most compelling validations of gravitational lensing, time-delay physics, and the predictive power of Einstein's framework. His work now stands as a cornerstone in gravitational lensing research. His equations are taught in advanced astrophysics courses. His name is spoken alongside the most important observational milestones of our time. And most importantly, his vision of a universe so interconnected that light from one moment can arrive again and again, carrying secrets of space and time, has become a vivid reality. The legacy of Sir Refsdal is not just that he was right. It's that he imagined a universe capable of echoing its own events across the void. He saw the cosmos not as a fixed tableau, but as a dynamic theater, where light bent around corners and time could fold back on itself. And the cosmos, in return, whispered back to us through a delayed glimmer in a distant galaxy, "Yes, you were right all along." To witness something as precise and mind-bending as Supernova Refsdal, an exploding star replayed across the sky through multiple arcs of light, is to witness an event made possible by an extraordinarily rare alignment. This wasn't the result of luck alone. It was the outcome of a perfectly orchestrated cosmic geometry, a lineup involving vast structures of matter stretching across billions of light years, all positioned just right to allow Earth to catch a glimpse of light that had no business arriving here more than once. This moment, when galaxy cluster, and our planet align across unfathomable distances, is among the rarest in observational astronomy. The universe is vast beyond comprehension. In its expanse are billions of galaxies, each filled with billions of stars. In such overwhelming scale, alignments as specific and exact as the one that made MACS J1149 and Supernova Refsdal visible in this way are astonishingly uncommon. Think of it this way: to create multiple images of a single distant galaxy and one of its stars, the background galaxy must be positioned almost exactly behind a massive foreground lensing structure, a galaxy cluster, in this case, relative to our line of sight. And within that background galaxy, a supernova must occur in a location that sits within the highly magnified region of the lens's caustic curves, the very boundary where lensing becomes strong enough to duplicate the image. On top of that, Earth must be located at just the right angle to witness the diverging light paths arriving at different times. A slight deviation, if the background galaxy were a few arcseconds off, or if the supernova had occurred in a different arm of the spiral, or if our vantage point were tilted a degree differently, could mean we'd never see a multiply-image supernova at all. The images would merge into one, or the event might be undetectably faint, or the time delays too brief to distinguish. And yet, in the case of MACS J1149, everything lined up with such precision that not only did we see it, we could predict it. This rare cosmic geometry is governed by the gravitational lens equation, a mathematical framework that connects the positions of the source, the background object, the lens, the massive object bending the light, and the observer, us. That equation is complex in practice, because real-world lenses like galaxy clusters are not simple spheres of mass. They are sprawling, chaotic collections of galaxies, dark matter, gas, and substructures, each pulling on space-time differently. To create multiple strong-lensed images, the source must lie near or across what's known as the critical curve in the lens plane. These curves are not circles. They are contorted, web-like shapes that reflect the mass distribution of the lensing cluster. And in the case of Supernova Refsdal, its position in the host galaxy happened to fall across one of these critical curves. That's what allowed it to be lensed into 4 nearly symmetric images forming the Einstein cross configuration in 2014. And more astonishingly, that same event was lensed again, its light redirected through another region of the cluster, to reappear in 2015 in a different part of the sky. All of this happened because the spatial relationships between the supernova, its host galaxy, the lensing cluster MACS J1149.5 plus 2223, and Earth were aligned with breathtaking precision. Such alignments are so rare that only a handful of known supernovae have ever been multiply-imaged through gravitational lensing. Most strong lensing events that we observe involve static objects, galaxies and quasars, whose light is constant or only subtly variable. Supernovae, by contrast, are brief. Their light rises and falls over weeks or months. That temporal nature makes the alignment even more fragile. If the timing were off, if the supernova occurred earlier or later, or if we hadn't been observing that region of the sky when it happened, we might have missed the opportunity entirely. It's like catching a meteor precisely when it streaks through the sky, but with the meteor's path bent by planets, stars, and invisible matter. Moreover, the alignment was not just a happy accident. It was one astronomers had hoped for, searched for, and finally found thanks to decades of survey data and the unparalleled observational power of the Hubble Space Telescope. Projects like the Cluster Lensing and Supernova Survey with Hubble, CLASH, and the Frontier Fields program were specifically designed to scan deep into the universe using massive galaxy clusters as natural lenses. These programs targeted clusters like MACS J1149.5 plus 2223 because of their known lensing strength, their ability to bend light significantly due to their mass. Without those efforts, the alignment would have gone unnoticed. The light would have arrived. The lensing would have occurred. But we would not have been watching. The uniqueness of the alignment becomes even clearer when we consider that MACS J1149.5 plus 2223 is itself a chaotic structure. It's not a neat spherical mass. It's an unrelaxed, merging cluster with subclusters and irregularities. That means the gravitational lens it produces is full of bumps, ridges, and twists, making the critical curves within it even more complex. Yet, somehow, the supernova's light managed to thread its way through these regions multiple times, creating observable time delays of days, weeks, even a full year. And let's not forget the alignment in time, not just in space. The fact that humanity happened to be watching, with instruments capable of detecting such subtle lensing effects, at precisely the moment when the light from a star that died 9.3 billion years ago was looping its way through space, that's astonishing. If this supernova had occurred a century earlier, it would have passed unnoticed. If Hubble had not been operational, if astronomers hadn't been scanning the lensing clusters with such persistence, or if the image data hadn't been analyzed with extraordinary care, we would not be telling this story today. Instead, the universe allowed us to catch a glimpse of its geometry in action. In a cosmos that is mostly chaotic and indifferent to our presence, this moment of near-perfect alignment reminds us that, once in a great while, everything lines up. Light, gravity, time, and curiosity converge to create something unforgettable. And now that we know such alignments are possible, they can be sought again. Future surveys from the James Webb Space Telescope, the Vera C. Rubin Observatory, and Euclid will scan wider, deeper fields of the sky. The hope is that more rare alignments will be discovered, more lens supernovae, more multiply-imaged galaxies, more echoes of cosmic events that let us read history from multiple perspectives. Each one will depend on geometries as rare and delicate as that of Supernova Refsdal. But this one, the alignment between MACS J1149.5 plus 2223, its background galaxy, and our planet, will forever remain a landmark. A moment when the invisible mathematics of the cosmos drew a straight line across billions of light years and allowed light from a single dying star to speak, not once, but many times. The moment astronomers realized they were witnessing a gravitationally lensed supernova, a cosmic event where light from a single stellar explosion arrived via multiple paths, at different times, creating several images, they knew they had entered uncharted territory. But seeing it was just the beginning. The next, far more intricate challenge was to understand how the light had traveled through the vast, twisted curvature of spacetime sculpted by the intervening galaxy cluster, MACS J1149.5 plus 2223. And to do that, they needed to build an accurate, high-resolution model of the lens itself. A gravitational lens may be a natural object, but understanding and predicting its effects requires some of the most complex simulations and mathematics in modern astrophysics. Modeling a gravitational lens is like reverse engineering the structure of an invisible, multidimensional sculpture. You start with scattered beams of light arriving from a distant source, each bent, delayed, and magnified differently, and then attempt to reconstruct the mass landscape that caused this. It's a bit like hearing echoes in a canyon, and trying to map the shape of every cliff, crevice, and overhang based only on the delay and distortion of sound. In the case of MACS J1149.5 plus 2223, the problem was especially challenging because the cluster is not a neat, spherical object. It's a massive, chaotic conglomeration of galaxies, hot gas, and most importantly, vast amounts of dark matter. The visible matter, stars, galaxies, gas clouds, only accounts for a small fraction of the cluster's mass. The majority is invisible, detectable only through its gravitational influence. That means the lens astronomers were modeling was largely made of unseen forces. To reconstruct this lens, astronomers relied on a combination of observational data, theoretical physics, and computational modeling. The first step involved mapping the visible structure of the cluster using high-resolution images from the Hubble Space Telescope. These images revealed the positions of hundreds of galaxies within MACS J1149, as well as the multiple arcs and images of background galaxies that had been stretched and bent by the cluster's gravity. Each of these arcs served as a clue, a trail of breadcrumbs left by photons that had been manipulated by the lens. The next step involved incorporating spectroscopic data, particularly redshifts. By measuring how much the light from each galaxy had been stretched due to the universe's expansion, astronomers could determine their distances and separate foreground from background objects. Knowing which galaxies were part of the lens and which ones were behind it was crucial to building an accurate model. Then came the heart of the process, using these observational constraints to simulate the mass distribution within the lens. This required both parametric and non-parametric modeling techniques. Parametric models assume the mass is distributed in relatively simple ways, such as assigning dark matter halos to each galaxy with known shapes and sizes. Non-parametric models, on the other hand, let the data speak for itself, using grid-based approaches to estimate mass in small regions, adjusting values until the predicted lensed images match the observations. But neither approach is perfect on its own. In practice, astronomers use hybrid techniques, combining the physical assumptions of parametric models with the flexibility of non-parametric mapping. These models are tested and refined using software packages like LensTool, Galactic, Grail, and WSLAP+, each offering different algorithms to interpret the gravitational lens. One of the most critical constraints in the MACS J1149 model came from the positions and time delays of Supernova Refsdal's multiple images. These acted like calibration points. If the model predicted the wrong arrival time, or if it couldn't reproduce the observed positions of the Einstein cross, it was incorrect. So astronomers iteratively adjusted the mass distribution, adding substructures where necessary, tweaking galaxy halo shapes, altering the location of dark matter clumps, until the model accurately reproduced the observed light paths and time delays. In essence, they were sculpting the invisible with the chisel of mathematics and the brush of light. Once the model was refined, it achieved something truly astonishing. It predicted the future appearance of the supernova. Based on the geometry of the lens, the model indicated that light from Supernova Refsdal would appear again, this time in another part of the sky where a different image of the host galaxy had been lensed. The prediction was precise. Astronomers knew the general location and could estimate the timing to within months. This prediction became a defining test of both the model and of Refsdal's original theory. And when the supernova reappeared in 2015, just as forecast, the model was validated in one of the most public and scientifically satisfying ways imaginable. But the implications went even deeper. The accuracy of the lens model meant astronomers could now use it not only for Refsdal but to explore the entire background field. It became a gravitational telescope of sorts, a calibrated lens through which distant galaxies and cosmic events could be studied with incredible magnification and clarity. Faint galaxies too distant to be seen normally could be detected and analyzed, their light amplified by the cluster, and their images bent into arcs and spirals. And every successful lens model also contributes to our understanding of dark matter, since the placement and behavior of the mass needed to produce the lensing effects often differ from the locations of visible matter. If a galaxy contributes less to lensing than its brightness suggests, or if a seemingly empty region of the cluster causes unexpected deflection, it points to concentrations of dark matter. These discrepancies offer one of the only direct ways to map dark matter's distribution in space, making gravitational lensing models essential not just for cosmology, but for particle physics. The MACS J1149 model stands as one of the most detailed lens reconstructions ever made, and Supernova Refsdal played a key role in shaping its accuracy. It's a perfect example of how a transient event, a momentary flash of light from a dying star, can leave a lasting imprint on our understanding of the universe's architecture. It also exemplifies the strange duality of observational astronomy. On one hand, it requires passivity. We wait for the universe to present phenomena on its own schedule. But on the other hand, it demands precision, patience, and creativity in how we interpret what we see. The photons from Refsdal traveled for over 9 billion years. But it took the human mind, armed with physics, computers, and determination, to bend those photons into meaning. Now, that model continues to be refined, updated with new data from instruments like the James Webb Space Telescope, which provides deeper infrared imaging and sharper resolution. As more lens supernovae are discovered, new light paths can be traced, new mass structures identified, and the lens model improved. In a very real way, this modeling effort is like drawing a map of a mountain range from echoes. Each delay in light is a bounce, each arc an outline. And with enough echoes, we begin to trace the shape of something we cannot see, something vast and invisible, and yet, somehow, knowable. What made the successful observation of Supernova Refsdal, and the predictions surrounding it, so astounding wasn't just the cosmic coincidence of gravitational lensing. It was the fact that pulling off this feat required an almost impossible interplay of timing, position, brightness, and modeling precision. Every part of this discovery was hard, exponentially harder than what most astronomical observations demand. And yet, against the odds, it all worked. To understand why this was so difficult, we need to look at the convergence of three incredibly fragile variables: when the light would arrive, where it would appear in the sky, and how bright it would be when it did. Let's begin with timing. Gravitational lensing delays are measured in days, weeks, sometimes even years. But these are not neatly packaged or predictable without intensive modeling. The path that a photon takes when traveling through a lensing cluster isn't just a straight line, it's a curved, distorted trajectory through warped spacetime, stretched or compressed by the gravity of all the mass, visible and dark, within the cluster. Some light paths pass through deeper gravitational wells and are delayed more, others might skirt shallower regions and arrive sooner. When the Hubble Space Telescope observed Supernova Refsdal's Einstein cross in 2014, astronomers realized there was a possibility it would reappear later through another lensing path. But how much later? The answer wasn't obvious. Depending on how the mass was distributed in MACS J1149.5 plus 2223, the arrival time of the next image could range from months to years. Without knowing the precise layout of dark matter in the cluster, the prediction would be little more than a guess. Timing, then, became a race against uncertainty. Astronomers had to build and refine mass models of the cluster based on every gravitational lensing clue they could find. Each arc, each distorted galaxy, each offset in position between lensed images of background objects contributed to narrowing the range of possible delays. They used several independent modeling teams, each using different assumptions and algorithms, to cross-validate predictions. But even with all that effort, the timing estimate wasn't exact. The predicted window for the supernova's reappearance ranged from late 2015 to early 2016. To catch it, astronomers had to plan for constant observation over that span, an expensive and logistically challenging task, especially when telescope time on Hubble is one of the most precious and competitive resources in science. Then came the problem of position. The reappearance of the supernova would not be in the same place as before. Each image of the supernova was tied to a different image of its host galaxy, a galaxy that itself had been split into multiple arc-like versions scattered across the field of view. The supernova wasn't just traveling through different corridors of time, it was showing up in different projections of the galaxy. Predicting exactly where within those projections the supernova would appear was an exercise in pinpoint accuracy. If you were even a few tenths of an arc-second off, fractions of a pixel on Hubble's detector, you might completely miss the brief flash. It would be as if you aimed a camera at the sky hoping to catch a single firefly reappearing after a year, without knowing which blade of grass it might land on. Astronomers had to identify which lensed image of the host galaxy would contain the new appearance. They examined the spiral arms, clumps of star formation, and internal structure of the galaxy as it was mirrored across the lens. By matching features, like cosmic forensic detectives, they traced the supernova's position in one image and mapped where that same point would fall in another. Only then could they focus Hubble's instruments on the right part of the sky. Finally, the third challenge, brightness. Gravitational lensing can amplify or diminish the brightness of an object, depending on the path the light takes and the magnification gradient in the lensing region. The four images in the Einstein cross were relatively bright, enough to be detected and studied with confidence. But the predicted 2015 reappearance, known as image SX, was expected to be dimmer, due to the shallower gravitational potential of the path that light had taken. If the supernova were too dim, it could be lost in the glare of the host galaxy. Worse, it might fall below Hubble's detection limit altogether. And since supernovae rise and fall in brightness over weeks, missing the peak could mean missing the entire event. If astronomers mistimed their observations, they'd only capture the tail end of a fading light curve, losing critical data that would help refine models of both the supernova and the lens. These three elements, timing, position, and brightness, each carried their own uncertainty, and each required near-perfect alignment to yield success. And they had to be solved in unison. You could get the timing right, but miss the position. You could find the position, but the brightness could be too low. Or worse, you could get all three right and still miss it due to gaps in telescopes' scheduling or instrumental issues. Despite this, it worked. In late 2015, just as predicted, the supernova reappeared in the region of the sky astronomers had targeted, with the brightness roughly in line with expectations. It was faint, but unmistakable, a ghostly flicker that had traveled through a different route across space-time, arriving after all the others. It was a resounding confirmation not only of the gravitational lens model, but of the extraordinary coordination among dozens of researchers and institutions. Teams across the globe had worked together to build the models, calculate the delays, prepare the observations, and respond quickly when the light finally arrived. The fact that they managed to do all this with a supernova 9.3 billion light-years away, seen through a cluster billions of light-years closer, is nothing short of miraculous. But the success didn't just come from brilliance, it came from perseverance. Every step had demanded patience, refinement, and a willingness to trust in theory even when faced with uncertainty. It showed that human ingenuity, combined with nature's own gravitational tools, could overcome even the most staggering observational challenges. And now, the template has been set. With each new lens supernova discovered, astronomers will revisit these challenges, timing, position, brightness, and face them again. But thanks to Refsdal and the experience of Max J1149, they'll be doing so with a new sense of possibility. In the face of a universe defined by complexity and distance, this event stands as a testament to what can happen when science, precision, and persistence meet. It worked, not because it was easy, but because every difficulty was met with a deeper determination to understand the cosmos. Imagine standing in the middle of a funhouse of mirrors, not the kind that simply reflect, but one where each pane of glass stretches and twists your reflection differently, and sends it back at you after a delay. In some mirrors, your image appears instantly. In others, there's a strange pause, a lag of seconds, or minutes, before you see yourself move. Now imagine that instead of your reflection, it's a supernova, and instead of mirrors, it's the warped fabric of space-time itself bending, delaying, and reshaping the light from a single distant explosion. That's exactly what happened with Supernova Refsdal. Its light was split across the universe, not by mirrors, but by the colossal gravitational field of the galaxy cluster MACS J1149.5 plus 2223. And just like a funhouse, the result was not just multiple images, but multiple moments, staggered and distorted, each carrying the echo of the same event from slightly different paths through the cosmic maze. To visualize these light echoes, you have to first understand what it means for light to take different paths. Photons, massless particles of light, usually travel along straight lines in flat space. But when space itself is curved by massive objects, like stars, galaxies, or especially galaxy clusters, the paths curve as well. In gravitational lensing, those curves aren't just deviations in angle, they're distortions in time. Because light still travels at a constant speed, a longer or deeper path through curved spacetime takes more time, just like a winding mountain road takes longer to drive than a straight highway. With Max J1149, this effect was turned up to an extreme. The light from the supernova's explosion was bent and redirected by the gravitational field of the cluster, forming multiple corridors through which the light reached Earth. These weren't just different angles, they were different routes through the gravitational contours of the cluster. Each path had a unique length and gravitational depth, and so each light echo of the explosion reached us at a different time. When astronomers observed the 4 images of Supernova Refsdal forming a cross-like shape in 2014, they weren't seeing the explosion happen 4 times. They were seeing one event, arriving through 4 time-staggered corridors, each shaped by the invisible mass of the lensing cluster. And even more astonishingly, in 2015, another image of the supernova appeared in a different region of the sky, having traveled a completely different path through another section of the gravitational lens. Each image was a piece of a temporal puzzle. The 2014 images arrived almost simultaneously, having taken paths of nearly equal length. The 2015 image, however, had taken a longer or more gravitationally complex route, arriving a full year later. This means that, from Earth's perspective, the supernova flickered not once, not twice, but 5 distinct times, 5 delayed echoes of a single moment. The funhouse metaphor becomes even more vivid when we consider the shapes of the images. The gravitational lens doesn't just delay light, it magnifies and distorts it. The images of the host galaxy in which the supernova occurred appeared stretched into arcs, some curved like ribbons or crescents. The supernova itself was compact enough to appear as a dot, but its location within these arcs further illustrated how gravity was twisting the geometry of space. If we could step back and watch the light from Supernova Refsdal as if we were floating above the cluster, we would see something remarkable. Photons radiating outward from the explosion, some heading in straight lines, others veering sharply, some curving tightly around massive galaxies, and still others plunging through deep wells of dark matter. Each route would carry the same signal, but with varying arrival times and magnification. The entire process would resemble a cosmic hall of corridors, some fast, some slow, all ultimately leading to Earth. Astronomers have created simulations and visual models of this process, showing how the light cones from the supernova spread out through warped space. These simulations reveal that what looks like simple repetition is anything but. Each echo of the supernova is unique. One image may arrive first but be faint. Another may come later, stretched in time and magnified. A third may be blurred, bent around multiple galaxies. And yet, all of them originate from the same explosion, the same dying star, the same brilliant outburst billions of years ago. This phenomenon is not only visually stunning, it's conceptually revolutionary. For centuries, humans thought of light as something static, a ray, a line, a single moment. But what gravitational lensing shows us is that light is more than that. It's a medium through which the geometry of the universe expresses itself. The photons from Refsdal didn't just travel, they experienced the contours of space-time. Their journey, their delay, their distortion, all tell a story of the matter, visible and invisible, that shaped their paths. And for us, watching from Earth, it's like receiving postcards from different routes of the same road trip. Each one shows a different view, a different timestamp, a different curvature of the same explosion. We're not just seeing space, we're watching time unfold in parallel, each light echo revealing a slightly different version of the same past. This is perhaps the most mind-bending part of gravitational lensing. It doesn't just distort space, it distorts causality. The supernova happened once. It released its light once. But because of the paths that light took, and the way space-time is curved, we can watch it multiple times. We can see it unfold, rewind, and replay, not through simulation, but through the raw, natural behavior of the universe itself. In a broader sense, this tells us something extraordinary about the universe. Events are not fixed points in time. They are waves that spread outward, manipulated by the shape of the cosmos. And when that shape is just right, when the cosmic funhouse is perfectly aligned, we can see not just the past, but the many versions of the past. This realization opens the door to an entirely new way of thinking about observation. We're no longer passive recipients of light from distant stars. We are time travelers, catching glimpses of history as filtered through the warped tunnels of gravity. Each echo is a message not just from a star, but from the fabric of reality itself. And in the case of Supernova Refsdal, those echoes were so precise, so clearly tied to the explosion's known light curve, that they allowed astronomers to listen to the universe in stereo, to hear the same song played on multiple delay lines, each version revealing something new about the space it traversed. As we move forward, astronomers hope to detect more of these echoes, more lens supernovae, more temporal corridors, more paths through which light can tell its story. With telescopes like James Webb and Rubin Observatory, the funhouse will become clearer. The hallways will multiply. And the echoes of stars long dead will continue to arrive, one delayed glimmer at a time. In all of humanity's centuries-long study of the stars, we've grown used to certain rules of the cosmic theater. Stars are born, live, and die. Light travels in straight lines unless acted upon. Time moves forward. Supernovae, those rare and cataclysmic deaths of massive stars, are spectacular, yes, but brief and final. Once the light reaches us, it's over. A flash, a curve on a light chart, a memory in data. Until Supernova Refsdal. Until MACS J1149. Until a galaxy cluster's gravitational grip bent not just the direction of light, but the very rhythm of time itself. Because what astronomers witnessed with Supernova Refsdal was not a typical cosmic event. It wasn't merely something seen from a distance. It was replayed. Naturally. Unforced. Not simulated on a computer or inferred from models, but genuinely reseen, delayed by nature's own hand, through the warping of space-time by gravity. The supernova didn't explode again. It didn't loop like a video file. It happened once, 9.3 billion years ago, but due to the paths its light took around the enormous mass of the galaxy cluster MACS J1149.5 plus 2223, we saw it more than once. We saw its light arrive in separate moments, separated by days, weeks, and even a full year. The universe itself pressed rewind. To truly grasp how rare and astonishing that is, you have to appreciate the scale involved. This wasn't light bouncing off a nearby mirror. It was ancient light, from a dying star at the edge of the observable universe, traveling across unfathomable voids, encountering a massive gravitational lens, a structure of galaxies and dark matter that just happened to be aligned precisely between the star and Earth. That lens didn't just bend the light. It twisted space-time so acutely that different streams of the same light traveled different distances and arrived at Earth at staggered intervals. It was as if the universe handed us multiple versions of the same postcard, each delivered on a different day by a different cosmic courier. But it wasn't just about the delay, it was about the naturalness of the event. Prior to this, we'd theorized such phenomena. We'd even seen hints of it in lens quasars, which fluctuate in brightness and thus appear to vary in different images over time. But those were active, repeating systems. This was a one-time cosmic explosion. And we saw it more than once, not because we created the effect, but because gravity itself is the effect. The laws of physics, foretold by Einstein's theory of general relativity a century ago, had choreographed a performance for us, a stellar death split across time and space, unrolling like a cosmic film reel. When the light from Refsdal reached Earth in 2014, it appeared in the form of 4 images arranged in a cross, symmetrically surrounding a foreground galaxy, what's known as an Einstein cross. Each image was a different projection of the same explosion, the same light traveling slightly different paths, hitting Earth at roughly the same time but from different angles. That alone was stunning. But then came the extraordinary moment in 2015, when astronomers observed another image of the supernova. This wasn't just another angle. It was a replay. The light had taken a significantly longer route through a different part of the lensing cluster. And it arrived, almost a year later, exactly when scientists predicted. The explosion had happened only once, but the cosmos showed it to us again, like a natural time-lapse. This was cosmic scale rewinding, a literal loop in time caused not by science fiction, but by the very real and very measurable curvature of space-time around mass. It was like watching a documentary about a star's death, pausing it, rewinding, and playing it again, but through a telescope, with light that had spent billions of years in transit. The implications of this are enormous. First, it proves, visually and unambiguously, that time can be manipulated on cosmological scales through gravitational lensing. Not in the sense of sending someone back in time, but in the very real sense that information, in this case, light, can arrive out of sequence, depending on the geometry of mass and spacetime. It confirms Einstein's predictions about the relationship between gravity and time. The deeper the gravitational well, the more time stretches. And when you combine that with the distances involved, you get light paths that stretch into different temporal realities. Ones we can observe, if we're lucky enough to be looking in the right place at the right time. Second, it gives astronomers a tool unlike any they've had before, a way to study the same transient cosmic event more than once. Usually, if a supernova happens and we miss the early flash, it's gone. There's no going back. But with events like Refsdal, we can literally rewind the clock. We can see the rising light curve from one image, then compare it to the delayed echo from another image. That's like having multiple camera angles on a single, ancient cosmic event. Third, it gives us a dynamic view of the universe's gravitational structure. By comparing when each light echo arrives, scientists can reverse engineer the mass distribution of the intervening lens. It's like sending a sonar ping through the cosmos, and reading the results based on how long the echoes take to return. And because some of that mass is dark matter, completely invisible except through its gravitational effects, this technique becomes one of the few ways we can actually map it. And finally, on a more philosophical level, it shows us that time in the universe is not rigid. It is elastic. Not in the way we experience it on Earth, but in the way light travels across the universe. Events may be fixed in their own moment, but the way we perceive them is shaped by the geometry between us and them. Supernova Refsdal didn't just show us a star dying, it showed us the death of a star echoing across space-time, rippling along multiple corridors, each curve a page in the story of gravity and time. There's something haunting and beautiful about seeing light that's already passed us once return for a second visit. It reminds us that the past is still out there, literally, in the form of photons traveling the cosmos. And under the right circumstances, with enough gravity in the right places, we can see that past again. Not imagined. Not reconstructed. But genuinely seen. Light from a single event, arriving not once, but twice. The universe, with its warped valleys of space-time and its scattered pockets of invisible matter, has shown us that it can replay its own moments. It can send messages forward along tangled timelines, allowing us to glimpse what was, again and again. This was the first time such a natural cosmic replay had ever been seen. And because it was real, not theory, not simulation, but light caught and recorded, it changed the way we look at the sky. It proved that if we watch long enough, the past might visit us again. When we look back at the history of astronomy, at the milestones that mark human progress in understanding the cosmos, there are moments that redefine what's possible. The first telescopic observations of Jupiter's moons by Galileo. The discovery of cosmic microwave background radiation. The detection of gravitational waves. These are the pivot points where our perception of the universe expands dramatically, when new tools and ideas unveil realities we couldn't previously imagine. And into that pantheon of astronomical breakthroughs now enters MACS J1149. Not because it is the brightest, or the closest, or the most visually stunning galaxy in the sky, but because it became the stage upon which one of the most extraordinary scientific observations of all time unfolded, the first ever multiply-imaged, time-delayed supernova. A cosmic event that wasn't merely seen, but seen more than once, arriving in parts, spaced by time, through nature's own gravitational machinery. This single galaxy, nestled some 9.3 billion light-years from Earth, is now forever linked to one of the most important demonstrations of Einstein's general theory of relativity. It didn't just host a supernova, it hosted a moment of revelation. Before 2014, MACS J1149 was already of interest to astronomers. It had been catalogued as part of the Massive Cluster Survey, a collection of distant, massive galaxy clusters observed for their strong lensing properties. Its central cluster, MACS J1149.5 plus 2223, is so massive that it distorts and magnifies background galaxies, turning their light into stretched arcs and multiple projections. But even in a universe full of lenses and distortions, nothing like Refsdal had ever been seen before. That all changed when Hubble detected the Einstein cross, 4 images of the same supernova surrounding a galaxy within the cluster. It wasn't just the beauty of the configuration or the novelty of the observation that made this moment historic. It was what followed, the prediction of another image, a year later, and its successful detection in 2015. This was the culmination of decades of theory, of a prediction first made in the 1960s by Norwegian astrophysicist Refsdal, who had speculated that such an event could one day allow us to test both gravitational lensing and cosmological parameters. Max J1149 became the proving ground for that idea. A distant galaxy and its dying star became the validation of a theory that had waited half a century to be confirmed. And in doing so, this galaxy was etched into the annals of astronomy, not just as an object of interest, but as a place where science achieved something unprecedented. It became, quite literally, a cosmic classroom. Its place in history is not merely symbolic. Max J1149 has become a reference field. Papers that explore gravitational lensing models, dark matter mapping, and cosmological expansion constantly return to this cluster and its host galaxy. When scientists build new lens models or test new software for simulating gravitational effects, they often calibrate them against the data collected from Max J1149. When new lensing events are discovered, they are compared against the Refsdal event as a benchmark. It has become a standard, a Rosetta Stone for time-delayed lensing phenomena. It's not just about the supernova either. The arcs and distorted light from Max J1149 have helped astronomers peer deeper into the early universe than would otherwise be possible. Light from galaxies behind Max J1149 is magnified and brought into visibility. Some of the most distant galaxies known were discovered in its lens field, young, primordial systems seen as they existed when the universe was just a few billion years old. That means Max J1149 isn't just a site of scientific victory, it's a tool, a naturally occurring telescope, turning our attention to regions of space and time that would be beyond our reach without it. And this is not a one-time moment frozen in the past. The cluster is still being studied. With the James Webb Space Telescope, the detail and depth of data from Max J1149 have entered a new phase. Webb's infrared capabilities allow it to see even deeper into the light echoes, galaxy structures, and subtle gravitational distortions within and behind the cluster. New features are being detected. More lens galaxies are being catalogued. Max J1149 continues to deliver, continues to serve as a cornerstone for modern astrophysics. In this sense, the galaxy's importance only grows over time. It's not just a historical curiosity, it's a living laboratory, evolving with every observation, every new data set, every refinement of our gravitational models. As long as scientists seek to understand lensing, dark matter, cosmic expansion, and the structure of the universe, Max J1149 will be revisited again and again. Its name, once just another designation in a catalog, now carries weight. When you say, Max J1149, in astronomical circles, it evokes precision, awe, and scientific achievement. It's become shorthand for what's possible when theory meets observation, when prediction meets reality, when a single dying star's light, bent and delayed, can reshape our understanding of the universe. And there's something deeply poetic about that. This isn't a galaxy that shines with unusual brightness or contains rare structures. It's not flashy in the traditional sense. It became famous because it happened to be in just the right place, at just the right time, aligned with the Earth and with a massive cluster that acted like a cosmic prism. Through that alignment, it became a vessel for one of the greatest observational triumphs in history. In a universe so vast, so full of galaxies beyond number, the odds of witnessing such a perfect event, where a star explodes, its light is split across space-time, and humanity just happens to be watching, are astronomical. But it happened. And it happened here, in this galaxy. Max J1149. Its place in history is assured not just by what we saw there, but by what we learned, and by what we continue to learn. It is more than a distant smear of light in the Hubble field. It is a symbol, a landmark, a cosmic monument to the power of curiosity, mathematics, patience, and the grand, graceful dance of gravity and time. The successful observation of Supernova Refsdal through gravitational lensing didn't just mark a thrilling chapter in the history of astronomy. It opened a window into the future of cosmic observation, a future where we don't just glimpse the universe as it is, but replay it. The implications are profound. What happened once by chance, an accidental alignment of a supernova, a lensing galaxy cluster, and our observational instruments, could one day become a routine scientific tool. A natural time machine, not just for one event, but for many. Because if we can find one star exploding multiple times across space due to the curvature of space-time, what's to stop us from finding more? Theoretically, this phenomenon isn't unique. It just requires the right geometry. There are billions of galaxies, countless massive clusters capable of lensing, and supernovae occur regularly in distant galaxies. It's just that only a few of them are perfectly aligned with both the lens and Earth to produce observable, delayed images. But as our telescopes improve and sky surveys become more sophisticated, we are now entering an era where these alignments, once considered fantastically rare, are beginning to surface more frequently. In fact, telescopes like the VERAC, Rubin Observatory with its legacy survey of space and time, LSST, are designed to scan the entire sky every few nights. It will detect thousands of transient phenomena, supernovae, variable stars, and perhaps most excitingly, lens supernovae and other multiply-imaged, time-delayed events. With its enormous field of view and rapid cadence, Rubin will not only catch these events, it might catch them in progress, seeing one echo first and predicting the arrival of the next. What was once serendipity may soon become strategy. Imagine the possibilities this creates. We may soon live in a world where a supernova is seen in one location, and then, using models of gravitational lensing, astronomers calculate where and when its next image will appear. Telescopes across Earth and in orbit are then trained on that predicted location, not to wait and hope, but to expect it. The cosmos will have a schedule. Time delays, once unpredictable, will become forecastable. And the applications stretch far beyond watching dying stars. Early galaxies, primordial quasars, and even population 3 stars, those first stars ever born in the universe, could be seen, not just faintly, but with repeated clarity. Gravitational lensing allows us to peer into the distant past by magnifying galaxies and light that would otherwise be lost in the darkness. With repeat observations via time-delayed paths, we could examine the same young galaxy more than once, seeing its behavior over time or from slightly different perspectives. This transforms gravitational lensing into more than a curiosity. It becomes an observational enhancer, a multiplier of cosmic information. Each lens becomes a kind of natural laboratory, a place where the curvature of space-time itself records and replays the history of the universe, frame by frame. And with new space telescopes like James Webb, Nancy Grace Roman, and future gravitational wave observatories, we're gaining the instruments necessary to capture those frames in exquisite detail. Think about that, a gravitational wave observatory like LISA, Laser Interferometer Space Antenna, operating in tandem with an optical lensing event, might one day detect the ripples of a cosmic explosion just as the light from that same event arrives through multiple paths. Multi-messenger astronomy, the study of events through both light and gravitational waves, could be enhanced by lensing, allowing us to reconstruct cosmic stories not just in stereo, but in surround sound. Lensing could even help us detect and study kilonovae, the mergers of neutron stars that produce gravitational waves and heavy elements. If a kilonova occurs behind a lensing galaxy, we might see it more than once, with each light path offering a unique window into the physics of such collisions. Imagine being able to study the same explosion multiple times, refining measurements, probing asymmetries, catching details missed in the initial flash. There's also the tantalizing prospect of using lensed events to improve our grasp on cosmological constants. The time delays between light paths depend not only on the mass distribution of the lensing cluster, but also on the overall shape and expansion rate of the universe. By accurately modeling lensing delays in multiple systems, we can make more precise measurements of the Hubble constant, the rate at which the universe expands. This could help resolve the current tension between different methods of measuring that constant, a growing mystery at the heart of modern cosmology. As our ability to model and predict lensing delays improves, we could even envision a kind of cosmic calendar, a catalog of delayed light echoes from various sources. This would let astronomers plan for future observations, knowing that echoes from distant events are still inbound. It's like knowing that in 5 months, at a specific point in the sky, the light from a supernova that already exploded will finally reach us via a longer lensing path. It's the closest thing we have to scheduling appointments with the past. And even further out, this concept might be applied to exoplanet research and black hole studies. If a quasar or active galactic nucleus is lensed and shows time-delayed flickering across multiple images, we can study the environment around its central black hole in more detail, testing theories about accretion disks, relativistic jets, and more. The concept of repeatability is critical here. In most of astronomy, events are single-shot. You see a star explode, and if you weren't looking at just the right time, it's gone. But lensing rewrites that rule. Suddenly, the sky isn't just a static canvas of once-only light, it's a dynamic, echoing arena where the past can return, where observation can be planned, and where chance can be tamed by knowledge. So what does this mean for the next generation of astronomers? It means they'll be trained not just to observe, but to predict. They'll learn how to interpret gravitational maps, forecast arrival times, and orchestrate telescope resources around these events. Astronomy will move from the reactive to the proactive. We'll watch the universe not just as it is, but as it will be, through echoes already traveling toward us from ancient explosions and collisions, just waiting to arrive. And maybe, just maybe, there will be a day when the replaying of cosmic history is no longer a rare and marvelous exception, but a normal part of how we study the sky. When the same supernova is studied a dozen times from a dozen light paths. When galaxies at the edge of time become as familiar as our local stars, because we've seen them, not just once, but many times. This is the promise that Supernova Refsdal and MACS J1149 gave us. A glimpse into a future where the universe is not just watched, but rewound. A future where light is more than illumination, it's memory, preserved in the curvatures of space and time, waiting to be discovered again. Even long after the cosmic curtain fell on Supernova Refsdal's encore performance, astronomers never looked away from MACS J1149. In fact, its role as host to one of the most remarkable natural experiments in gravitational lensing only cemented its status as a celestial laboratory, one that continues to yield secrets, data, and insight with every new observation. While the fireworks of the supernova may have drawn the world's attention, it's the quiet, constant glow of the galaxy cluster itself, MACS J1149.5 plus 2223, and its twisted arcs of light that have become the focus of relentless scientific scrutiny. These arcs, delicate and surreal, are far more than mere visual oddities. They are stretched-out images of galaxies that lie far beyond MACS J1149, warped by its immense gravitational pull. To the eye, they look like thin crescents, luminous ribbons, or mirrored smears curving around the cluster's bright core. But to scientists, each arc is a golden thread, woven through space and time, guiding us to galaxies that would otherwise be invisible, lost to distance, faintness, or cosmic redshift. What makes MACS J1149 particularly valuable is the clarity and structure of its lensing. Its mass distribution, though not entirely symmetrical, is well defined and layered, with both luminous galaxies and vast clouds of dark matter overlapping. This complex, multi-layered gravitational lens creates not just arcs, but multiple images of the same background galaxies, each arriving with subtle shifts in time and magnification. Studying these images allows astronomers to triangulate not only the source's position and light curve, but the mass and structure of the intervening lens itself, offering clues about the elusive distribution of dark matter that makes up most of the cluster's mass. Thanks to long-term observations by the Hubble Space Telescope, MACS J1149 has been mapped in extraordinary detail. Over years of study, astronomers have built highly precise gravitational lensing models of the cluster, iterating on them with each new set of arc data. These models are now among the most sophisticated in all of astrophysics, serving as templates for other lensing systems and as benchmarks for calibrating cosmological simulations. With each arc added, each redshift measured, these models gain fidelity, sharpening our ability to reconstruct the invisible. And it doesn't stop with Hubble. The James Webb Space Telescope, JWST, with its infrared eyes and unprecedented sensitivity, has begun turning its attention to MACS J1149, bringing a new layer of detail to its already complex portrait. Where Hubble could resolve the arcs and the supernova, JWST can resolve within them, breaking them into individual stellar populations, identifying emission lines that trace star formation, and even spotting the gravitational tug of smaller dark matter clumps hidden within the lens. This new level of granularity means that JWST isn't just watching the sky, it's performing forensic analysis on cosmic light that's been traveling for billions of years. In MACS J1149's lens background galaxies, it can study galaxies that existed less than a few billion years after the Big Bang, examining their structure, chemistry, and evolution. Because the gravitational lens magnifies these distant sources, JWST can observe things that would otherwise be too faint, transforming MACS J1149 into a launchpad for probing the dawn of galaxy formation. Beyond that, astronomers are now using MACS J1149 to refine techniques for time delay cosmography, a field that uses the time differences between lensed images to measure the expansion rate of the universe. Supernova Refsdal was the first practical application, but it won't be the last. With so many multiple images and arcs, MACS J1149 is a treasure trove for this kind of work. New transients, like supernovae and possibly even gravitational wave events, may still appear behind the cluster, giving us further chances to watch cosmic events unfold more than once and to tune our cosmological measurements with ever-increasing precision. Meanwhile, the cluster itself is being studied in greater detail. MACS J1149.5 plus 2223 is a beast, composed of hundreds of galaxies and enormous clouds of dark matter, stitched together by gravitational force over billions of years. Astronomers are mapping its structure, its temperature profile via X-ray observations, its velocity dispersions, and even the nature of its intracluster medium. Every measurement tells a piece of the story: how such massive clusters form, collide, and evolve, and what that says about the invisible scaffolding of the universe. Interestingly, some of the most recent work with MACS J1149 involves searching for lensed stars, not just galaxies. When a background star aligns perfectly behind the gravitational field of a foreground galaxy, its light can be magnified by factors of thousands, sometimes appearing briefly as a single, transient bright spot in one of the arcs. These events are rare and subtle, but they've been detected, and MACS J1149 is a key hunting ground. Studying such lensed stars can offer insights into both the structure of the star itself and the distribution of compact objects, like rogue planets, black holes, or even primordial dark matter, in the lensing cluster. This is where the story becomes both scientific and existential. We are looking at a region of space that doesn't just contain mysteries, it creates them, through the geometry of space and time. MACS J1149 has become a cosmic observatory, a gravitational laboratory, and a lighthouse that points the way into the deep, early universe. It's no longer a passive collection of stars and dark matter, it's a participant in our quest for knowledge, offering us the tools to peel back the veils of time. And the sky is far from done speaking. As technology improves, we will see more in MACS J1149. Fainter arcs, older galaxies, subtler time delays. And perhaps one day, another supernova, another cosmic echo, will burst forth from the background, splinter into multiple paths, and show itself in pieces across the lens, repeating like Refsdal once did. And when that happens, we won't be surprised. We'll be ready. Because we're still watching the skies. Still listening for the echoes. Still waiting for the light that left its origin long before Earth even formed, curved through the colossal gravity of an ancient cluster, and made its way to us. Not once, but again, and again. In the cold, quiet abyss of space, so still and indifferent, so vast it defies our most poetic metaphors, there came a flicker. A flash of light that should have been lost forever, swallowed by the distance, buried by time. A star had died. Violently. Beautifully. Its light surged outward in every direction, scattering into the infinite, its final message carried on photons that would never know rest. And against all odds, we, tiny, fragile, clever creatures on a pale blue dot, were watching. But what made this moment more than mere observation wasn't just the light. It was the echoes. The repetitions. The revelation that this star's final cry, though uttered once, could be heard not once, but again. Not because the star burned anew, but because space itself, shaped by the invisible hand of gravity, bent that light and gave it multiple paths. Multiple journeys. Multiple arrivals. What we witnessed was not a trick. It wasn't a simulation or an illusion. It was the universe playing itself again. A single moment in time, folded and stretched by mass and motion, arriving in different forms, at different moments, to the same destination. It's as though reality itself stuttered, and in that cosmic glitch, we found a truth deeper than imagination. Think about that. A star exploded 9.3 billion years ago. It ended its existence before our solar system had even formed. Before the Earth cooled. Before atoms in your body ever found each other. That explosion, an instant of unimaginable energy, was long gone by the time our ancestors looked up at the stars and wondered what they were. And yet in our era, through our eyes, we saw it. Not once. But again. And again. Each arrival of its light wasn't just a delayed postcard from the cosmos. It was a whisper from the past, shaped by space-time, curved by ancient mass, and delivered with eerie precision. A cosmic deja vu not of memory, but of physics. What does it say about our universe that such a thing is possible? That time, thought to be a relentless march forward, can ripple and fold through the geometry of space? That a single event can echo across the cosmos and arrive in our night sky more than once, each time bearing the same truth? It says that reality is not linear. It is layered. It is sculpted. And in its vastness, it contains mechanisms not of chaos, but of structure, laws so strange they appear magical, and yet so consistent they can be used to predict the arrival of ancient light like the ticking of a clock. We call it gravitational lensing. We trace it with equations. We diagram its paths in digital models. But at its heart, it is something primal, a dance between light and gravity, between mass and time. And in that dance, we are the audience. Witnesses to the echo of a dying star. Observers of a ghost made real not through belief, but through measurement. Supernova Refsdal was more than an astronomical event. It was a philosophical one. A reminder that the universe does not obey our need for simplicity. That what is gone is not always lost. That even death can linger, travel, reappear. That light, once loosed from its source, can journey for eons and still find new ways to arrive. And now, we know to look for it. We know that the universe has its mirrors. Its prisms. Its time loops. We know that when a star dies, its story might not be over. Not because the star endures, but because the space it illuminated can carry its message through more than one path, more than one now. So what happens next? We keep watching. We turn our instruments toward the heavens, not just in search of what's new, but of what's old, repeated. We hunt for echoes. We search for reflections. We study the sky with the understanding that sometimes, the universe doesn't just move forward. Sometimes it turns back, offering us not a second chance, but a second look. And in that second look, perhaps we will find more than knowledge. Perhaps we'll find humility. Wonder. A kind of poetry made not of words, but of light, bent, delayed, split across space-time, and offered to us like a secret finally revealed. Because in the end, when the universe repeats itself, it's not just physics at play. It's a kind of memory, woven into the fabric of everything. A reminder that time does not erase all things. That some moments, written in photons, live on long after they've passed. Waiting. Traveling. Ready to be seen again. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.